for attending this session. My name is Oscar Viahi, Storage Chair. I will start with a short presentation of what we have done in the past year at our storage committee, and then we will have two other presenters with short presentations about the solutions that we are demoing outside. Will be done by Jamin Bowen, my colleague, and Howard. Where's Howard?
Right here.
Oh, thank you.
Stack velocity.
Velocity. Thank you. All right. So without further ado, I go through. So everybody knows by now I'm chairman of the storage track. I give you a very short update. I talked about this in our joint session as well. These are the projects since I've been at the storage committee chair. We have been reviewed and approved. Two projects from Facebook. They have been reviewed, basically OpenWall version 08 and the storage hardware for cold storage version 07 by Facebook. Both of them have been reviewed and approved from storage committee as well as incubation committee. Then Intel mini server board that was reviewed and approved, as well as Seagate's storage device with Ethernet. We contributed basically the connector of Kinetic to OCP, and that has been approved. These are all official approved OCP documents. We have a Honey Badger going through the final acceptance, might get accepted in the next few weeks from Facebook. This is basically the small mini server that you can hook up to the Knox box and have the storage managed by that. I think Mike is here. He will do a presentation tomorrow. Then these are the documents right now contributed to storage committee, but not fully approved yet. The first one is the Nitro XP card that you can see outside. We are doing a demo, Ceph and storage, flash, and SMR, which Jamin will talk about. This is contributed to OCP. It is in process of being reviewed and approved and modified so that it reaches the expectation that OCP needs to have. And of course, today we will work on the CNI and the storage document. One project we have put on hold from a while ago. I talked to them. They said, for now, put it on ice. So if you go to Wiki, you will see this is on the on-hold projects. I've listed some links. These documents will be later on, of course, available to you. But one main thing I would like to emphasize is that we would like you guys to really get engaged with the storage team through the mailing list, through the wiki, through the certification process that we are working today, as well as if you're removed, and I think our sessions are also broadcast remotely today, you can form your meetups, local meetups, get together wherever you are, and then do some good hacks there. So we have a meetup site. You can go there, sign up, and then organize your own meetup. And how to join, I have listed the email list, mailing list. We have monthly calls. Again, on even days, it's on even hours. So if it's an even month, actually, rather, it's at 4 p.m. If it's odd month, it's at 9 a.m. all Pacific time. So that way we can cover the entire globe with that time frame. With that, call to action, we talked about that, collaboration, contribution, and consumption. So this is basically still very valid. And if anybody has any questions for the storage, if not, we are in a very tight schedule, by the way, I would like to repeat. So everybody gets 30 minutes, the main presenters. Jamin and Howard get about 10 minutes each, and we go from there. So I would like to call Jamin for doing his presentation, which is this, and you have to turn it on. Okay. Yeah.
All right. Thank you, Oscar. So I had a chance to talk with quite a few of you outside, which wanted to give you an idea of what we're showing in the open rack that's out there. And it's really a work in progress, so I'll give you some clues about where we're trying to go with this. So what we have outside is a Ceph setup that's leveraging 2 pieces of next generation storage. And when I say that, I mean explicitly we're using shingled magnetic recording drives, SMR drives, which you'll hear about a lot throughout some other sessions today, and PCIe flash. So if you're not familiar with Ceph, it's an object storage software piece that now is part of Red Hat that Intake developed. It's very powerful, and it allows you to have a huge cluster of commodity servers that has a number of commodity disk components inside of it and presents a single unified storage fabric. It's either object storage or block storage to the host. Very much is caught on inside of OpenStack and is getting to the point of production. Now, one of the so it basically serves objects to clients. It has peers perform the replication back and forth to have highly available configurations. And one of the other things that it does that's different than some of the other object storage products that are out there is it uses a strong consistency model. So in comparison to something like Cassandra, which is a eventually consistent model that you can use for certain applications and has very good scaling properties, Ceph uses a strong consistency, which means the client doesn't receive acknowledgement that the write's been committed until it's guaranteed to be durable in more than one place. And that's very important for certain applications as well, because you can obviously, if it's a certain cloud backup solution for free for clients, then eventual consistent previous versions of files is fine. But on some other applications, that's just not acceptable. So one of the things that has supported that is there's a journaling mechanism within Ceph where anything that's going to be written to the object storage service is written to another location first. And that's been kind of a fairly known use case of using SSDs to accelerate the Ceph journal. And so that's understood and that's known. The other thing that is relatively recent is this erasure coding of objects. So there's a basic ability to do redundancy within Ceph without having the triple mirroring. So the setup that we have outside, for instance, has 5 members in the Ceph, it's 5 OSDs with 3 of 5 erasure coding. So we can tolerate the loss of up to 2 of those 5 elements without any data loss. So it's basically a 60% parity overhead, and it's important to understand it's not like a traditional hardware RAID where blocks go from here to here to here. Everything is distributed everywhere. So the traditional problem that people have with really high capacity volumes, the rebuild problem, is solved because you can have thousands of disk drives. Each one has just a little chunk, and it just has to recover the redundancy for a certain number of objects. So even with 8 terabyte drives that we have in play, with a large enough cluster, even failures of an entire server would be trivial to rebuild. So that's Ceph by itself, and it's had a use case for Flash. What we added, and this is where we're trying to do more, is we're using SMR drives. And SMR drives have some interesting properties. First, they're cheap. It's very, very dense storage, and it's in many ways the future of disks because disks are pushing aerial bit density up. And they have excellent density, cost, excellent read performance across the board, and sequential write stream. But they have poor random write performance. Basically, you have to update huge chunks of the SMR tracks at once because they're shingled. They lay on top of each other, and you have to update a big area at once. So at the end of the day, poor at random write performance, good at everything else. Now, we've got PCIe flash in this demo as well, which there's several properties that make it nice. It's very high performance. It fits directly into the server, so it doesn't effectively take any space. And its only downside is it's a poor cost per gigabyte. Flash is more expensive. And what we wanted to look at is if we could leverage these two together to solve some of these problems. Because basically, we could use, we're already going to use Flash to accelerate the OSD journals. But the question we're asking is, can we isolate the SMR drives from the small block I/O? And what we're doing right now with this setup is we're putting some of the file system metadata, in addition to the journals, onto this PCIe flash board. And the flash board goes directly into the Winterfell server, and then we have an open vault connected to the other side with 15 SMR drives. So you can take a look at it outside, and by getting just the file system metadata, and then also by using this with Ceph, and using Ceph with erasure coding, it's already an environment that's not really optimized for small block random writes, because it's designed for a little bit more of an archive use case. So we don't think there's a lot of downside, that if you're going to deploy Ceph with erasure coding and use SMRs, we just have to get some of the leftover small block IOs off of the SMRs to just have it be a cost savings play. So that's what we have set up. This is out there running. And what we're looking to do is to grow this test environment with a few other levels. We've been using different file systems for the local OSD stores on each SMR drive. XFS has proven to be better than EXT for being able to eliminate some of the small block IO. We've already kind of optimized there, and we're moving the XFS journal onto the flash. What we want to add from here is we're going to add a filter driver that was developed in the past to try and isolate the leftover small block IO. So specifically, some of the indirects of the file system and some of the inodes that we couldn't quite just push to be redirected. There's 3 different filter drivers we're looking at. One is in-house. They all use Device Mapper as a filter. Flash cache that Facebook published, and also DM cache. And basically looking at modifying those so that they're not, excuse me, they're not a frequently accessed cache, but they're just trying to permanently isolate small random writes. Second, after this, is Ceph itself is adding a cache carrying capability. It's there now, but it's kind of in a little bit more of a beta mode, where you can have a high-performance flash pool, and then you can have a disk pool behind that that'll automatically migrate data between. And we think that's an obvious spot where we're using the flash for the journals. We can use it for some local file system metadata. If there's extra space left over, we can make an explicit high-performance tier. And then the last piece is this host-aware SMR plus flash. Since this is, if you're using this as a pure object storage, we're looking at could you use LevelDB, could you use something like RocksDB as the back-end storage local file system rather than XFS or ext4, and that would be perfect so that there's no small blocks that go back to it. So all of this is future work. We're showing the demo out here, and we're working with an academic institution and a commercial client on a much larger scale cluster, which if it's successful, they'll publish quite a bit of information about. So that's what we're doing, but it's interesting just to think of the scale of what's possible with these components now. So the way that we have it set up is we have one Winterfell with one flash card for each shelf of nodes. And you could adapt this differently. If you decide that you're not going to push the Ceph nodes as hard, you could have one Ceph node with 2 shelves and have 30 drives. But even at what we're starting with, it's amazing the density. And we have some of the pre-released SMR drives in the setup that are 8 terabytes each. So each shelf has 120 terabytes of storage, and each server has 2 terabytes of local flash. So it's about a little bit less than a 2% or 1% flash ratio to just isolate the journals to a small block room. Now when you look at the open rack with the multiple PDUs with 10 open U's per each, you end up with 18 OSDs and 33 terabytes of flash and 2.2 petabytes of SMR storage. And then whatever, you can add whatever erasure coding you want on top of that. So the 3 of 5 that we're doing out here, you would net out to about 1.5 petabytes of usable, fully redundant storage that is able to tolerate up to 2 of 5 elements failure without any data loss. So we think it's a really interesting technology demo of the next generation SMR drives, how flash is being leveraged, using all open compute hardware, and using some of the open source Ceph software. So hopefully, if you haven't had a chance to come out, we're just right outside, and we'll be happy to show you some of the details while it's running live. Go ahead. Yes.
Have you found that closing the stone right now offers value?
So it's
Repeat
not
the question, please.
Okay, so the question was, do we find that exposing the zoning in the host-aware helps improve the SEP performance over the driver? And so I'm less interested in the exposing of the zoning for the application to manage per se, because I'm kind of using the Flash to manage the small block I/O to begin with. What is more interesting to me is I want to be able to completely eliminate the drive level remapping so that I can write entire SMR chunks at a time. Does that make sense? Well, that it is. That's the objective that we have right now, but there's still the chance that, so I get the metadata off of it. I can't protect against small objects. So if I do a block level in SEP, then I have some control over the size of units that are written to the SEP drives. If I use an object level, then it's going to break it up into three pieces and add two redundancy mechanisms. And if it's a 1 megabyte object, that'll be 333K, 333K, plus 2 that are overlapping, which is still going to result in some small block I/O to my device, and it'll do some fragmentation on the SMRs themselves. So the whole reason to go to the host aware is to eliminate those edge cases to say it's perfect. If that makes sense. So that way I don't have to worry about some of the garbage collection ever occurring on the drive and not just tricking it with the filter drive. Right. That's what I mean. Right. I didn't. Okay.
Thank you, gentlemen.
Yeah, any other questions?
And Jamin will be here, so tomorrow as well. The station's there. If you have any questions or take a look at it, you're welcome.
Thank you.
All right. Next. All right. So that's.
That's right. Yeah. It'd be nice. I'll talk to you about my SEP presentation now if you'd like. Yeah. Is this working?
No.
Now is it working?
Yes.
Well, while he's playing with it, my name's Howard Cohen. I work for Stack Velocity, and this is our first introduction into the OCP community. Although I've been working on the OCP kit now for about 3 years or so through other jobs. So Stack is a here we go. So Stack is a division inside of Jabil, which is one of the world's largest contract manufacturers. And we are focused specifically on systems integration and design services for large-scale data center deployments. So today I want to talk about a new product we're showing today for the first time called Hattrick, which is our first OCP product aimed at this environment. But we have a lot of experience from the kinds of work that Jabil already does. We build for people like NetApp and EMC and IBM and a whole bunch of other people. So taking that experience learned in building very large scale, large volumes through other customers, we're taking that and producing it for ourselves. So Hattrick is an attempt to basically create a high density storage solution meant for Open Rack. So today, in an Open Rack scenario, you have a Knox-like object. There are a few other companies that have similar configurations, but essentially it's 30 drives, kind of fixed configuration in the rack. Well, a lot of the people that we deal with are not interested in 30 drives or even 15 drives. That's a bit much for them. And they're looking for other kinds of configurations that they can build. So what we're introducing is a family of products. The first one will be Hattrick MS. which is up to 12 drives in a sled with a microserver that currently will be the same one, the Panther Plus, which is now through the incubation committee and is part of Honey Badger and that system. Well, this is going into this system. It'll allow us to tie a 10 gig Ethernet mezzanine card into this and allow us to create a hot swappable drive system sitting 3 in one 2U environment up to 36 drives.
Like what I'm looking at here, it looks to me like you're going to pull it out and you're going to come off the bus bar.
This is what it looks like in that. But the next slide, I think, will answer all of your questions. But thank you for showing it. So here is how it will work in a rack. It has a tray that mounts into a single bus bar, a Open Rack 2 or Open Rack 1. And in the back of the sled, you will have hot swappable fans that you can get from the hot aisle. And then there will be cable arms that will allow power to flow to each of the 3 chassis. The 2 outer chassis face each other so that the drives can be taken out from the inside, and the central one goes in whatever direction. I think it's going that way, but not that way. It's going one way. It will, as I say, be able to be powered from a single power bar on there, and there will be a cable management will be dealt with on the arms. So the actual unit itself will consist of, like I said, up to 12 drives sitting up there. Each one will be hot swappable. This part will be for a Panther Plus card, and this spot right over here is meant for an Ethernet card, which will allow you whatever connectivity options that you want to have. So it's a pretty simple thing. This is just a metal prototype to at least give you an idea of what it is, and it will slide into its tray, hook in with the arms, and be able to come out enough to be able to get every drive swap. We will be showing this in our booth upstairs. This, as I say, is the start of things. We're looking at, we can turn this into a 15-drive JBOD in the same thing, and we can make 10-drive versions, whatever size people want. We want to basically be able to build a solution that will allow people to pick the kind of configuration that they need, not the kind of configuration, the only configuration they need. So that's essentially what it is. The expectation that this will be available sometime Q2. Please.
Choose which bus bar I have to pull power from, or am I forced to use one or another?
Yeah, the central bar is the one. The central bar is what we're going for. In most of the racks going forward, the outer 2 bars will be disappearing. So the central bar is the best option. But essentially, from our point of view, although I'm not actually doing the power control board, but it wouldn't matter which one you pick from as long as it's we are assuming going forward, people will be going to a single bus bar.
All the rest of the tenants, no tools, easy swap, etc., are all built in.
They have no choice but to be.
Really? Yeah.
So these guys, by the way, will be sitting on a rail inside. So each one of these sleds will be mounted on a rail to be able to come out there. So it will be able to be held outside the rack securely, and without we're spending a bunch of time worrying about vibrations and all of that you have with this kind of orientation. So and we have some experience in building cabinets that not like this but similar to this. So yes, and we also have a good understanding of the central rules, the tool list, the cabling. There will be a cable management solution that will mount to the front of this that will allow you to go run your Ethernet cables or SAS cables into this box. We're working on. We'll probably have several different options for that depending upon the environment. So we have a lot of experience in dealing with large-scale data center needs, and we'll make this as easy as possible to maintain in it.
And get rid of 1 or 2 more of the drives in front, slide full of mini ITX port in there, and make it a proper service.
Possibly. it's not, right now that's not something in our plan, but if you want to buy hundreds of thousands of them, talk to us. We
That is
are.
the answer everyone gets. Please do not use that answer.
Physically, we can do anything. If we can build the version with the 12 drives, building something with a larger board, a different board orientation that fits in there is trivial. The hard part is getting n number of drives working. Getting n-3, not a problem.
Yeah. What's the backplane that the drives are attached to? Cables or plane?
Plane. Plane. So they will, in the real version, you'll open it, the drives will push out. There'll be light pipes associated with each drive, so you can get status information as you're dealing with it. There will be lights on the front panel that will allow operators to go to the unit that needs work. All of the normal things that the metal prototype doesn't have will be
planned for 24 gigs, so SATA, SSDs in there, places, these things, caching server, etc.
Actually, I don't know the answer to that question. I don't know to what it's being spec'd right now.
That was also a leading question in the sense of
Please. Yes. So you want more of a 2.5-inch form factor instead of a 3.5-inch form factor?
No, I can cope with the 3.5. There's a bunch of 3.5 stuff showing on the floor tomorrow that high density is.
Sure.
So that's fine. But back into between, it doesn't give my problems.
Okay. All right. We'll take that into account. One of the reasons that we're showing this today is, first of all, we wanted to introduce Stack as a player in the OCP space. So that's the first thing. That's my first market. The second thing was, we're in the process of designing a lot of the specifics of this right now. Any feedback that we can get from anyone, we'd appreciate right now. I'd rather know about issues upfront than find them out when I go to production day one. So if anyone has any kinds of comments or any kind of ideas or things like that, please feed them back to us. I won't guarantee that we'll listen. I won't guarantee we'll do anything. I guarantee we'll listen.
At least go through Hive submitted a few, was that 4 years ago?
Yeah. Yes. Well, I come from Hive. The torpedo was just a. It was a paper diagram. It's one of the reasons why I wanted the metal here. I wanted to at least show you that we can at least have prototype metal data. Yeah, I think in particular with OCP, it's really hard to differentiate between trial balloons and things that people are getting serious about. And we are seriously building this thing. We have engineers that are working on designing it right now, and so we are committed to build this, to take this to production.
On 12 gig, right?
Excuse me?
On 12 gig.
Yes. Yeah, I don't know about 24. It's frankly something that I've never asked. So,
Well, we use.
but I think, yeah. Well, thank you. I appreciate it. I'll pay you off in the hallway later.
Thank you, Howard. Thanks. All right, so.
That's it. Oh, wait. Oh, yeah, this one.
Oh, you want this one?
This is what
Let's see.
So,
if you just introduce yourself.
Cool. All right. I'm Mark Carlson. I work for Toshiba, but I'm not here to tell you a bunch of Toshiba stuff. I'm here to talk to you about a new effort that's going on in the SNIA around object drives. And so I'm going to talk about that. What are object drives? Well, we're changing the interface from your SAS or whatever SCSI-based protocol to one that's based on IP from a SAS or SATA or fiber channel connection to Ethernet network. In some cases, there's key value semantics. That's what makes it an object and object store. And in other cases, it's going to be hosted software to put your object storage node down on the drive. For instance, Ceph was talked about earlier. So what's driving the market for that? Well, there's a number of scale-out storage solutions like Ceph that allow you to sort of scale incrementally. Instead of forklift upgrades, you can add a sort of building block approach to scale out performance, availability, and not have to forklift upgrade a huge systems. Hadoop's HDFS does this. In addition to Ceph, you've got Swift, and you've got the Kinetic open source project. There's a number of commercial examples such as Scality and CleverSafe. For those solutions, you'll see a lot of it. Commodity hardware this week here at the show. You're basically creating an object storage node with CPU, networking, and N disks in an enclosure. Although that is more inexpensive than the storage systems that have been out there in the world, it's not a very efficient way to do it. It doesn't really reduce your long-term costs, ownership's costs, and you have to do a lot of hand-holding. So here's an example with a Ceph architecture. You've got these Ceph OSDs, and there are various physical manifestations of an OSD, but almost always there's an enclosure with multiple hard drives in it. And then you've got the Ceph monitor, and you've got the Ceph metadata server in a cluster. If you throw object drives in here, now instead of a bunch of networking and enclosures and whatnot, everything's just talking to the drive itself, whether this is the Kinetic protocol or it's the native Ceph protocol. You're basically getting rid of a whole bunch of hardware and a whole bunch of software in the middle of that. Here's an object with Hadoop, an example with Hadoop. Hadoop has these data nodes that are doing replication and so forth. Hadoop has a name node where you do metadata and whatnot. And if you put object drives into that situation, you can also eliminate that. And one last example is Swift. Swift is the object storage component of OpenStack. And Swift has a proxy server, an auth server, and a number of other servers that can run anywhere, really. Auth servers typically what they call Keystone. But the client is writing to a proxy. It's not writing to the object servers directly. And it's the proxy's job to then parcel out the objects to the various object servers, do replication. In the future, they'll be able to do erasure code across those object drives and so forth. And again, if you replace those with object drives, in the case of Kinetic, the current implementations I've seen has the object node still up here. What do they call it? I forget the acronym for it. But eventually, this is all pushing down into the object drives. So what do you need? Well, with a new market segment like this, you're seeing that every vendor is doing their own kind of thing, right? There are no points of interoperability here. And so, what we really want to be able to do is have multiple vendors produce something that interops with each other. So SNIA has a good history of solving that. So we created a new technical work group. We'll come up with some sort of object storage spec and specs for drive-hosted software. We've got a good number of folks from the storage industry out there in that group participating. We have a meeting next week in Las Vegas, so that's coming along. We've come up with some requirements, just very high level. The physical form factor, we're not really paying that much attention to. Everybody wants the standard 2.5, 3.5 inch drive form factors. Electrical and environmental, this has to do with the connectors. similar to the Seagate proposal to OCP. Now there's an effort going on in the SFF group, which is Insights, ANSI. And so we're coming up with a pinout for your SAS3 type of drive that will swap out the SAS signaling for Ethernet signaling and be able to work with the OCP specification as well. Discovery and management, including capabilities. If you're going to load some software down in the drive, what does that look like? Security, assignment and ownership, configuration. You may be configuring the software that got loaded as well and set up, and then use of the drive. So again, the physical layer requirements, we're going to point to other specs, that describe that, including probably some of the ones from OCP. So we're not going to, SNE is not going to make a standard in the physical layer requirements. In the electrical environmental, I already mentioned that for the SAS3 type drives, we are working with the SFF group, but people see PCI connections as well for object drives, so we don't want to prevent that. So we push that out to SFF. Discovery management. This is something that we probably will pay attention to because SNE has a good history of doing storage management type standards. So when you first bring an object drive in to an already installed system, how does it know what kind of drive it is? Can I load software? What kind of software load? How big is the CPU? How big is the memory? How much networking does it have? And how much storage? So those are all kind of things that we're trying to get and refine requirements for over the next short period of time. And then there's a number of different usage requirements. In the case of Ceph and Swift, they've published actual information on their websites that say, I need this size of a CPU. They make little sort of configuration rules, like they say, for each terabyte of storage, you won't kind of like want a gigabyte of memory. So depending upon how big the drive is, as far as capacity is concerned, you may need more or less memory. But I think it's a little bit finer than that. Obviously, if you have solid state media under there, you may need a little bit more memory than you do with something like SMR. So we want to be able to talk about intra-drive protocols, but we're not going to solve the problem between Ceph and Swift, right? They're going to have their own stuff. It's largely determined by code, not specifications. It looks like Kinetic will do the same thing, mostly by code, not specifications. And then when your software lands on the drive, what kind of environment does he have to talk to the storage? Is that a key value, right? Or is you have to have a file system, and then you have to have SCSI drivers, and then you're talking SCSI inside the drive? Who knows? I imagine that'll be the start of things because their software is already written, like ButterFS and all these other file systems, to think in terms of block storage, right? But since they themselves are doing object storage out to the rest of the world, if we had an object storage underneath their software, that may make their software cleaner, more simpler, more performant, and so forth. Or you can load your own interface code. So it could work on top of the object protocol and instead of POSIX, which is file system or blocks. And then is key value enough? I mean, key value is very simple, it's sort of minimal kind of object interface, but what if you want to handle metadata? What if you want to do services down there on the drive, right? What if you want to do replication, archive, data protection, that kind of stuff down on the drive? Especially as the data gets colder that you put on that object drive, you're not going to need as much CPU and memory as you did when it was hot, right? Well, what do you do with that CPU and memory after the data on that drive gets cold? Well, maybe you run other services on it to do more sort of data services, more information services that were going maybe extract some metadata from the files, maybe allow you to run big data analysis on the data that's on that drive. There's all sorts of possibilities in that space. And then we have different ways of deploying stuff down there. You've got your data center network, compute, optional storage fabric, and then storage device. As far as Kinetic is concerned, they have an object API here, and that goes straight on to the data center network. There's other solutions where you load in your software and your apps, quote unquote, are sitting on top of Linux, on top of POSIX, on top of SAS Saturn, and you have your actual drive. So this is just sort of loaded host software. But there's other combinations as well. It doesn't all have to be in the same box. And it's not clear that putting a CPU not per disk is the right approach, at least right now. There's going to be a bunch of different things thrown against the wall and see if they stick. And then this kind of thing where all you have is essentially a proxy where you've got Ethernet coming in. This is like Swift's proxy server where you've got objects coming down and objects going in the back. Any questions so far? Yeah.
I'm kind of confused. Let's switch it to a quick back and forth. I got Honey Badger, and I got 15 or 30 drives, so I've got a net adder of 18 watts and 1 OS to manage. You're trying to tell me I need to do a net adder of 32 watts and 30 OSs to manage? Why would I?
So the question is, why would you exponentially increase the complexity of managing a whole bunch of software and money in different places? Is that right?
Yeah.
Well, you have that problem today in a large data center, right? And so you're going to have to solve that problem if you want to scale out anyway. Having that software close to where the data is, closer to where the data is going to give you some benefits, but then that comes at a cost, right? Because it does increase the management complexity. Now you have to upgrade that software that's in all those nodes, right? You may have to, when Kinetic version changes, you have to update a bunch of software as well. And this isn't a matter of reducing complexity. It's really a matter of what is the right architectural positioning here of where the compute is and where the storage is, right? And it's been going in this direction for a decade now, right? The whole scale-out OSD type of approach is already taking that. This is taking it down to the next level.
Yet all of us hyperscale are disaggregating as fast as we can, get away from the time capture. So I'm seeing you saying, okay, yes, but maybe tier 2, tier 3 could use this not server.
So the question is, you wouldn't do this. You're proposing you wouldn't do this for tier 1. But if I have SSD media behind an object drive, why wouldn't I put it in tier 1?
Sorry, not storage tier 1 data centers, people, Amazon, Facebook's versus Microsoft, Boeing or corporate environments.
I'm sorry, I can't rephrase your question, but you're saying that in the enterprise data centers they wouldn't do this, but more in the other way around? Okay.
I couldn't see the scaling successful to nowadays. I could see the scaling to ahead of them. That's a pretty big gap.
You have a question?
So the question originally was, how is this going to help me in my hyperscale? And And what I'm hearing your answer was is it's not going to do anything for the hyperscale. It might for maybe small medium.
No, I didn't say it wouldn't do anything for you in hyperscale. I think the problems that you're concerned about are being solved outside of this domain. They're already distributing, probably thousands to tens of thousands, right, of OSD devices out there, right?
Tens of thousands.
And now you're going up to another meg, and the tools are going to have to accommodate that for sure. I agree.
I'm saying.
Yeah, a Honey Badger might be the right point right now for deploying your stuff, right? Which is sort of a bigger CPU, bigger memory, bigger networking in front of a bunch of disks, right? But over time, as things get cheaper, as mass-produced disks with CPU and networking and whatnot on, the equations change. Other questions? Yeah.
You said that storage is exactly for the developing skills. Can you more better why in the previous line you said that the object storage is mostly based on hierarchy?
Object storage is based on interface?
Ethernet.
Oh, Ethernet. Ethernet's just, remember I said it could be PCIe as well. And it's really, it's taking it up from blocks, right, past the files all the way to objects, right? And through Ethernet, you can do object storage, right? Which means that you find an IP address for the drive, you use RESTful puts and gets to the drive of objects or partial objects. I guess I'm not answering the question. But that's why Ethernet, at least for now, right? But certainly we expect PCIe be there, especially for SSD type object drives. Other questions? Yeah.
Any thoughts on that scenario?
I don't know what Rapid I/O is. Okay. One last thing is Huawei has come to the twig talking about a key value framework. And this would allow you to basically take multiple vendors' drives and plug them into a framework that then on the top of the framework would have a standardized interface. So you don't really care what drive protocol is because everybody can run an adapter to their particular drive protocol. And then the framework kind of is the one thing you talk to if you want to come in with a file system or S3 or block. But that sort of, that's a different approach than standardizing on a protocol. You just standardize on the API and then let different vendors have their own sort of protocol sorted out at the bottom. And that could be an interim step before we get a standard protocol. So here's the link, the Object Drive Twig. We have a lot of people joining that. It's completely open. And we'll be publishing our stuff as we go. That's it.
Thanks, Mark. We have about 10 minutes. I had to do a little bit of shift of schedule. Mark, your presentation would be at 3. Sorry about that. So how about having like 5-minute break if you want 5 minutes break? The next session is joint session with certification team to go over the certification document. Okay. So 5 minutes.
Can I say one thing just before everybody leaves? After the joint session, we got moved to 3 o'clock, but we're going to talk about a really interesting architecture that's way different than anything you've seen. So please make sure that you come back.
Okay, yes.
So where do we want to go, left or right?
No, you are staying here.
They will come?
Yes, they are coming here.
Perfect.
Joint session will be here. All right, 5 minutes.
Come back after 5 minutes again.
By the way, thank you so much for doing this. What's your name? Michael. Michael, thank you so much.
Took me a while to actually get it because they were like,
Yeah, I was gonna leave.
but yeah, glad that you can join.
Please do.
That way I can see.
Okay. Yeah, exhibits.
Karifa.
Yeah, there is there's breakfast. What I meant is that on the website it was 7 to 9:30. There was still next class, but they will show up here, but they will have to keep it.
I'll ask you.
Open it and they can.
Well, I meet the guys giving us a hard time.
I'll warn you just a couple minutes before.
Yeah. You're dancing. Good job, though. Thanks. You have a dance issue.
I bought these socks, I didn't realize they were like,
This is all today?
yeah.
Oh, yeah. We have some tonight, right? So. That's a, right? You'll be back after, right? Oh, you did it. Why don't you just go? Yeah, I got it yesterday. Oh. That's the old joke. I walked up to the
It's all right, I'm gonna win this call.
Sorry, I'm moving around.
You're making me crazy.
Stress test. How you doing, man?
Yeah, let's get this.
No, there were people here before? No, almost every time. And two more times.
So,
If you don't mind.
Just 1 or 2 more minutes.
You want one? Yeah.
Is that okay? It's just. Sure.
Right. So we had to do some traveling with the schedule, guys. Sorry about that. Because the certification team is not ready. They will be here at 3, so we swapped. So I introduce Mark Goros and Jay, and they will have. Okay. So your mic is here. Then I'll give it to you. Go ahead.
Okay, thank you. Well, I think we lost some people anyway, but we'll go ahead and try. Jay and I are here today to talk to you about architecting highly efficient web-scale cold storage for unstructured data. But in getting to that cold storage, I want to tell you a little bit about Coringo, which is kind of behind this whole thing. So my name is Mark Goros. I'm co-founder and CEO of Coringo. Back in 2005, when we started the company, everybody was just starting to digitize the world. There was more structured data than unstructured data. But we realized that there had to be a better way to start storing unstructured data. You may recall, going back that far, that to store unstructured data was just as expensive as storing structured data. So the big iron vendors were cleaning up on people storing more and more content. And we realized that had to change. So what we did is we took a completely fresh look at this problem. And we said, why use the same tools that we've been using for years to store files when we're trying to store a different class of information? So we threw out the file system entirely. File systems were designed 50 years ago and were designed for wholly different purposes than people are using them for today. So we decided to take a fresh approach and build a massively symmetric parallel architecture with no file system whatsoever. We write directly to the metal. There's no inodes, there's no file system, there's no overhead associated with a file system. Let me give you a couple of examples. France Telecom was storing email, about 40 million email accounts on NetApp filers. And they could only fill the NetApp filers 35% full. Do you know why? File system overhead. There's a lot of cases where file systems start maxing out at 1.5 petabytes, and we can't go any further. So why have file systems underneath object storage systems? Why not get rid of that overhead and go directly to the metal? So in 2005, we invented this pure software object storage model, arguably the world's first software-defined storage product. And the idea was to store metadata with the data, eliminate complexity. Complexity, you were talking about complexity a little while ago. Complexity is the bane of our existence here. You know, the more complex things are, the more things can break, the more difficult they are to configure, the more difficult they are to scale. Let's get rid of as much complexity as we can. Our product first shipped in summer of 2006. We're on version 7 right now. And version 7 is a beautiful place to be for a software product. Basically, you're far enough along in your life where a lot of the bugs have been driven out, but there's still plenty of headroom for features, for functions, for performance, for new things to happen. We have clusters out there in our customers. We've got hundreds of customers worldwide. We've got clusters that have been running 5.5 years without stopping. So this is a rock solid product doing very well out in the field, shipping version 7. We consistently try to innovate in terms of efficiency, simplicity, performance, and data protection. That's what Coringo is all about. So a lot of different customers worldwide, some big, some small, and they all have many, many different use cases. But interestingly, they all have similar goals. They want to radically simplify their infrastructure. They want something that they can afford, affordability, and affordability as you scale. They want unstructured data storage that can actually span up to web scale. It could be small, it could be medium, it could be large as well. Why not use the same infrastructure for each? And the data must be searchable, it has to be accessible, it has to be protected all the time. Just a couple words about some of these customers. The Department of Defense Medical Health System for the Army and Navy is the second largest medical image repository in the world. It's up to about 16 petabytes today, growing to about 24 petabytes. That's based on our technology. Netflix in Europe serves up a lot of movies based on Swarm, Caringo Swarm. Verizon has 4 petabytes of Caringo Swarm, and they use it for internet abuse. They'll track literally hundreds of millions of events a day and do analysis in real time on those events, all in Caringo Swarm. Telefonica and British Telecom are both building, or both have built, Amazon S3 compatible storage services based on Caringo technology. There's a couple of reasons for that. One is the Patriot Act. They were afraid to store data in the United States. But the other reason is because they wanted the most powerful, flexible, scalable object storage infrastructure they could find, and they found it in us. Telefonica recently published that they're going to grow to about 75 petabytes of storage in South America and about 53 petabytes across Europe. The FBI also uses our technology for their evidence locker, and I can't really say anything more about it because it's above my pay grade after that. But Ask.com, Match.com, the City of Austin, St. Jude's Hospital, lots and lots of different use cases, all with the same goals. Cost-effective, reliable, scalable storage. So let me tell you a little bit about our technology. First of all, the base node or server that we run on is a classic x86 type server. NIC, CPU, RAM, disks. You can use any kind of disks you like, SATA disks, SSD, SAS disks, it doesn't matter. But this is the base foundation of what you need to run Swarm. Now, we never install any operating system or any software on the disk. We actually leave up to 98% of your disk available for storage. That's really what you want in a storage company, right? You don't want operating systems on there. You don't want to have to update operating systems and put file systems and fix file systems. Let's get rid of all that complexity. We deliver the software that net boots, and it is based on a Linux kernel, but it's a shaved down Linux kernel that you don't pre-install. It installs automatically with the software, and the software never is installed on the disk. We run everything out of RAM. All software runs out of RAM, all the indices are in RAM. It's a bare metal, booting from bare metal, simplified approach, no file system, no RAID, no single points of failure whatsoever. Each node can be configured differently. They can be multiple vendors. You can mix and match generations of hardware, and you just add nodes, basically boot one node, boot a second node into the same subnet, and within 90 seconds, that node is up and running and participating with the first. Boot a third, it's up and running and participating with the others. Build another one, boot another one up, and you built a swarm. And that's what a swarm is. And interestingly enough, in our swarm architecture, every node runs the same code. There are no special purpose nodes, no single points of failure, no bottlenecks. Every node can do all functions. This is kind of interesting. If you want to do erasure coding, if you want to do replication, if you want to do worm storage, if you want to do legal hold, every node is capable of doing every operation. Very different architecture than anybody has talked about today. So all nodes perform all functions. The cluster gets faster as you add to it. All nodes are running the same code, and it's very easy to expand because you don't have to worry about special purpose nodes, special rings, or anything like that. Now our model is based on a very pure object basis. Metadata, that includes system metadata, user metadata, whatever you want to put in, and life points, which I'll explain in a second, are grouped together with the data and encapsulated in an object. There is no metadata database. There's no separate place to go to find your data. You don't have to go to a metadata database first and then go find the object again. In fact, to find an object takes 0 IOPS. And we're pretty unique about that. All our indices are in RAM. As I said, we don't put any software or indexes on the nodes, on the disks themselves. And as a result, you can find your data with 0 IOPS, no matter where it is. This pure object model unlocks your data from applications, from hardware, from location. And that gives you true data portability. This means you can now use data in new ways that you never thought about using it before, because it's completely encapsulated. The authentication is encapsulated with it, the security is encapsulated, all the information about it is encapsulated in that object. Finally, we have something called elastic content protection. We have patented the ability to store erasure-coded and replicated objects in the same cluster, in the same node. Now, this makes a lot of sense because the value of data changes over time. And this is a key point here. Data value changes all the time. And when data value changes, shouldn't you change the way that data is protected? You can specify in life points in the metadata, and the system will automatically take care of this for you. Let's say you've got a very popular cat video, and you want to give it massive capability of tens of thousands of people seeing it very quickly. Maybe you make 50 replicas of that for 30 days. And then after 30 days, nobody really wants to see the cat video anymore. You cut it down to 5 replicas. And then after another 30 days, you erasure code it to 5,2 or 10,6 or whatever erasure coding you want. Mix and match in the same cluster, automatically handle it and manage it from life points in the metadata. You can shift between replication and erasure coding whenever it makes sense to reflect the value of your data. Now, one of the ways that we do this, one of the ways that we keep our swarm balanced, and we have all these capabilities, is through something we call the data market. The data market is a way of bidding. Each node, excuse me, each node actually knows what it's doing at any point in time. Bids are willingness to write, to update or retrieve objects, and the bids are affected by the state of the volume, how busy it is, how much space it has, how much RAM it has, I/O queues, the load, what's going on. All those values are rolled up into a bid. And the bids are given to a town crier, and the town crier spreads it across the cluster so that every node in the cluster knows the bidding state of every other node. So if you make a request to the cluster, let's say you want to write a request, and you go to any node in the cluster. Now, this is also interesting. There is no access node to the cluster. Every node is an access node. You can go to any node at all. So go to any node, that becomes your PAN or your primary access node, and you tell it you want to write this object. Well, if that node doesn't have the room, it knows who does. It'll do an HTTP redirect, give you to the node that can take that request, connect you directly there, and then you actually do your operation. It's a very efficient process, and bidding allows us to do automatic load balancing. It allows us to do things like super fast volume recovery. Now, here's another example. Let's say we have a cluster with 1,000 disks, and let's say you're using replication, 2 replicas to protect your objects, just for the case of argument. And 1 disk goes bad. Now, the replicas from that 1 disk are evenly spread across all 999 other disks. And each disk, when they get a red alert that a disk is down, it knows what objects were on that bad disk. It will re-replicate only those objects it has someplace else in the cluster. So replication recovery becomes parallel, distributed, and very, very fast. The larger your cluster grows, the faster recovery gets. It's a very interesting process. Now, bidding also enables us to do something called darchive. And darchive is one of the points that we're getting to in this presentation. Darchive is the key to cold storage. Simply, it's the patented capability, it's adaptive power conservation that spins down drives and reduces CPU utilization. Not that big a deal. I mean, we've seen companies do this kind of thing before, but it makes a lot of sense. When you're storing a lot of information, some of that information will not be accessed all the time. And wouldn't it be nice if those disks that that information is on quiesced and got quiet and went to sleep? The CPU ratcheted down. That would save power. It would save cooling. So darchive will automatically work in any kind of a cluster that you're using with Caringo Swarm. You can also assign specific nodes, or what we call subclusters, to be darchive nodes. They'll act something like disk drives. They spin up a drive, fill it up, spin it down. Fill up the next drive, spin it down. Fill up the next drive, spin it down. When all the drives are filled up, the node will go to sleep. That is a true darchive node, and that enables us to do some pretty interesting things. In a recent win, a 30 petabyte cold archive win, we actually proved 70% savings from power and footprint, 70% in monthly TCO savings, just because of archive. And I'll go into the details of that a little later if we have time. But why in the world are we talking about this? Why is this even important? If you believe the pundits out there, by 2020, we're going to have between 7 and 40 zettabytes of information that we're storing, most of it unstructured. That's an insanely large number. That's just a crazy number. But nevertheless, that's a lot of data. Now, it's great for all of us in here because we're in charge of storing it and analyzing it and taking care of it and managing it. So it's a great business opportunity. But for the people actually running those data centers, it's a little bit of a nightmare. The truth is, companies of all sizes are amassing large amounts of data. And remember, data is the basic unit of value here. Data is the value, not the hardware, not the infrastructure, the actual data itself. It must remain accessible. The value of data changes over time. The access patterns also change as the data ages, but the value may diminish, but it doesn't vanish completely. Never vanishes completely. And if it does, at some point, maybe you will delete it. But otherwise, we tend to hang on to data as long as we can. The perfect solution for this is what we think of as responsive cold storage. So let's look at some of the pioneers in cold storage today. Amazon, they have something called Glacier. It advertises 11 nines of durability, and it stores your information for long periods of time at a very reduced cost. They don't make any claims about how fast you can get it back, but it is cold storage. So that's Amazon. Facebook has something called Sub-Zero. They have dedicated two data centers to this. The storage servers power off when they're not in use, and they make, or they say they have the equivalent of 2 backups of data. But I have to tell you that within 3 years, I bet your company is going to have its name here, because everybody is building these huge repositories of tremendous amounts of unstructured data. You don't want to have them all active all the time. I'll show you why. Let's look at the cold storage requirements. A minimum of 11 nines, just like Glacier. The equivalent of 2 backups, like Facebook. Power off the servers when they're not in use, if you possibly can, like Facebook. Optimized very simply for efficient use of data center space, fewer racks, dollars per gigabyte, and watts per gigabyte. So what are you going to use? Caringo Swarm at scale is extremely efficient. Caringo Swarm, even in a small data repository, is also very efficient. It's a single pool of shared resources. You plug it into a network, boot up, and it's up and running in 90 seconds. The storage automatically deploys and balances. It's self-balancing, self-healing, self-managing, and it manages the metadata, the operating system, access, storage. There's no metadata database, no single points of failure whatsoever. It's very straightforward, very simple. Your other choices are ring architecture, like Swift, for instance, among others. The ring architectures use file systems underneath, and you have to set up an operating system, you have to set up metadata, you have to set up storage systems, you have to, your metadata storage is a single point of failure, so you have to duplicate that or make that redundant somehow. You have to make sure that it's protected with RAID, probably. You need separate rings for every type of protection that you want to use. Replication, every type or flavor or erasure coding, 5,2, 5,3, 10,6, they're all different rings. You have to manage all those rings separately. You have to manually migrate data separately. You have to manually balance and tune each one of those rings separately. You can certainly do that, but which infrastructure would you really want? Well, let's go a little deeper into that question. Let's look at a 3 petabyte cold archive, for example. And we'll compare Swift and Swarm to this, a ring architecture to the Swarm architecture. So for 3 petabytes, for reliability, you want at least 11 nines, right? For the storage, we're going to round it off to 3.86 petabytes usable storage. For a building block for a chassis, we're going to say 72 drives, 72 6 terabyte drives per chassis, just for argument's sake. And racks require 10 chassis per rack. If you look at Swift, Swift uses 3 replicas to get 11 nines. They need 9,258 petabytes raw for the storage in order to get 3.86 petabytes. 22 chassis, 3 racks, and 1,543 drives. That's the infrastructure needed with a ring architecture. Swarm, on the other hand, using 10,4 as an erasure coding protection, is actually 12 nines. We only need 4,320 petabytes raw, 10 chassis, 1 rack, and 720 drives. Already, just because of architecture, we're saving a lot of bits and more. 5 petabytes of storage space, 12 chassis, 2 racks, 823 hard drives. That's a tremendous saving just in terms of hardware and footprint. But wait, there's more. I always wanted to say that. At 100% operation, which in a theoretical world is a great way to start filling your cold archive because it has to start someplace, you're with Swift using standard enterprise drives, you're burning about 13,503 watts. Now, Western Digital has these drives called AE drives, and Jay is going to come up in just a couple of minutes and talk about those AE drives, and so I'll let him describe those to you, but they save a tremendous amount of power. In this case, you can see that they actually save about 4,000 watts of power. So even using Swift with AE drive, Western Digital AE drives, you're saving a tremendous amount of power. Throw Swarm into the mix, and you're actually down to about 4,387 watts. That's 5,000 watts less than Swift at 100% ingest. So already you're saving hardware, you're saving footprint, you're saving watts. Now let's start making that cold archive. 75% operation. This realistically is probably more the way that you're going to ingest in this particular cluster because it's very hard to fully have a cluster running at full bore all the time. At 75%, Swift, well, it can't spin down, so it doesn't even participate here. The numbers stay the same. Swarm goes down to 2,592 watts. And at 10% operation, the real cold archive, and I say 10% because sometimes you want to check the health of objects, and sometimes there'll be a request for some object. So we'll say 10% operation, you're down to 698 watts. That's like a 95% savings over what Swift is doing. We're saving watts, we're saving footprint, we're saving power. This is, I think, a very interesting illustration of what can be done with architecture. And now, Jay, if you come up and talk a little bit about the AE drives, that would be great.
Sure. Thanks, Mark.
Jay. No problem. I need less than that. So, while Mark and his Coringo team work on the system level architecture improvement, WD is striving to improve the component level efficiency. One of the features we developed recently is called the progressive capacity. Essentially, it's a manufacturing and product lifecycle management innovation allow us to get more from the same component. And in the just, what it does is that per drive, we can squeeze more capacity out. And also with the lifetime of this drive, it can grow when your component technology improves. As a result, is that the customers like Coringo can stay with one platform without new modification, get more capacity out of it. And also, because we can use the same platform and so for multiple markets, using this innovative features, we are allowed to use the common components process for longer and broader. These are the gist of the benefits of the progressive capacity. More engineering size. And you all know, not every part is the same, even if you place the same order. And the progressive capacity we adopted is a selective tool to allow each component optimal they perform, get the best out of it. Today, we're talking about many components in hard disk drive, and when we go through the manufacturing process, it will fall down to different buckets. For example, we only sell today the integer number of capacities, 4 terabyte, 5 terabyte, 6 terabyte. If we do the way as is, many of the drives follow. In this case, average capacity of each component is 6 terabyte. But we have discrete sellable capacity. So in this distribution, you will see half of the drive will sell as 5 terabyte, while half of them sell as 6 terabyte. you have a lot of excess capacity and not able to utilize it because of this constraint. And what we do is that we educate each component, add more buckets. We can align with the new architecture. The system need to be able to use the different capacity, as the Kringle system showed. And by doing this one, we'll go to the next page. How can get more capacity out? And the progress capacity happens at two phases. Number one is fixed time, like we call PQ1, stands for production order one. When we launch a product, instead of fixed capacity in the past, 50 of them, 5 terabyte, 50 of them, 6 terabyte. If you sell 2 products to a system, they got every 5.5 terabyte. By introducing the progressive capacity, we allow to create more fine granularity buckets. On average, when we ship the whole box of drive to the customer, they get the full distribution of capacity potential. In this case, we do achieve the average of 6 terabyte. And this is almost 10% of capacity gain for barely no additional cost to the customer if the software are able to accommodate the variable capacity. And what's more is that when time goes on, usually your process, your components improves. Today, if we fix the model, we sell the same product time over and over again, we always get the same ones. With progressive capacity, we are able to tap into the incremental gain of capacity. So the second quarter, when we get better components, so on and so forth, we get 100 gigabyte more. And all these incremental benefits adds up. Just the Kringle systems analysis showed those capacity increase translate better utilization of their chassis, capacity, power, footprint, so on and so forth. So it's a self-evolving product lifetime cycle management tool. And all this one is complementary to all other great features that us and other hard disk drive manufacturers are doing, like SMR, like more disk into it. They are all complementary. So that is my update for the team. And I'll give the control back to Mark.
Thank you. Thank you.
Thank you.
Just one more slide. So just as a summary, we think that Kringle Swarm with WD-AE drives create responsive and responsible cold storage, responsive in real time to application and user needs, responsible in the way that it saves power, cooling, and data center footprint. Darchive is the key that Kringle brings to cold storage power saving, and add that up with the WD-AE drives, and you've got the best of both worlds. Thank you very much.
Any questions for Mark?
Comment instead of question?
Yeah, sure. Go ahead. Hold on.
The whole concept of cold was really to separate from the archive use case. The reason we didn't use the word cold was there are so few of these workloads where you can take a production copy and an offline copy. So that would be perfectly fine for archive, i.e. you can spin it down, i.e. what Facebook is doing, and what you mentioned there. But if you look at the other use cases, the 90th percentile out there, you've got things like the Pelican system that tries to do heat and power load balancing, etc. The workload that comes to cold is non-predictable from your consumer point of view, so you cannot expect to be spun down more than 10% of the time, 20% of the time. We're still guessing. So I encourage you to drop the word cold from this and just go ahead and admit it's an archive.
Well, we just added the word cold for this presentation.
Sweet. Marketing at its best.
Sorry. So,
I would think another question would be...
Sorry, just one second. But you're absolutely right. You really can't predict those kind of things. And so you do need the capability of spinning down is really, really important because you have to save the power. But, you know, who knows how much you're really going to save.
Mark, follow up, I think I have one question, and that would be, what do you think as far as, you know, participating in OCP and open community, because the solution that you described looks very interesting. So is there any plan you or your team contribute part of it, some of it to OCP?
Yeah, we would love to get more involved in OCP for sure. That's why we came, you know, to this session to learn a little bit more, to find out. We would love to see about getting involved.
Great.
It's on your hardware compatibility list.
Okay.
Any other questions? All right, thank you very much.
Thank you.
So our next presenters are David and do you see that? Yes, yes. No, you have, so you can look up there. You have escape. Does it work? So you have this one.
So while those guys are hooking up the laptop, since we're late on the presentation, I'll just get going here. My name is David Burks. I'm the product management director for Kinetic open storage products at Seagate. So for those of you who aren't aware of Kinetic, Kinetic is a platform. It's a drive, but it's more than a drive. It's really a platform that we launched probably more than about a year and a half ago in terms of conceptual launching and so on. And includes an overall framework that includes an open source API, a new logical interface to what we hope to be eventually a class of devices called Kinetic drives, which are running on an Ethernet platform, TCP/IP being the electrical connection to the drive, and then a logical interface is a key value interface. And so we're moving toward this period of time where we're going to have an open source forum. We haven't decided the specific forum for that, the management of that open source API, but that's moving forward. We've had one public meeting so far, and so we hope to have more information on that in the future. As we've done this, I wanted to just start with going through the agenda here. So what we want to talk about is benchmarking Kinetic Swift and traditional Swift, because we're to the point now where our OpenStack Swift is working well on Kinetic, and so everybody's like, okay, how does it work, right? And so we've got some material to present on that today. Before I go into that, let's go to my first slide here. I wanted to just provide some context about why people are excited about this. And everybody sells TCO in the cloud business, right? We're going to save you money somehow or another. So this is basically, just some of our analysis about how Kinetic really can, save you money. And what we're doing is we're essentially taking storage servers out of the data path from the traditional, top rack storage server that's running your object management software, whether it be Swift or Scality or SAP or whatever. And we're putting, those small little microprocessors on the drive and take that responsibility for what those storage servers used to do. And so this was a one instantiation of ours. Add all the numbers up for all the hardware that you bought, put it in a spreadsheet, and look at it. So we believe that kind of in some of the worst case scenarios, when I say worst case, that when you compare a traditional system to a Kinetic system of the same density, so that you've got the same number of drives and JBODs and so on, that we're in the area of at least 10–12% total cost of ownership. Usually we get 5, 6, 7% CapEx, and the rest of that's an operating expense. And then go to the next slide, Neil. Some of the systems, when you have a far less denser system like a traditional one compared to a newer one, this particular one we modeled with a CIO of an object management software company who was recently sold, by the way. And we worked those numbers directly with them, and there's some really impressive numbers that are possible out there. So this is why customers are really interested in this, because it actually has a real significant opportunity to not only save upfront dollars and how much you're paying for software, for hardware, it also saves your power expense, and then there's a whole bunch, there's a green field out there in terms of some of the operational advantages you would get, architectural advantages, software advantages, and so on. So for example, the next drive that we're going to have is going to be based on an SMR drive, and we're going to abstract that SMR complexity, whether it be host managed, hostware, whatever. Kinetic front end takes care of that, and now these software guys are having to deal with this, don't have to deal with it. So that's some of the real value proposition around it. So today, what we have available, go ahead, go to the next slide, is a few of the ingredients are coming together. So several chassis are available now, Sanmina, Supermicro, Highbroush. We got a Seagate one that's coming in the 4th quarter. We've got software available now in the context of Swift. We have Scality coming. We have Nexenta, OCP-Storage, and Ceph, all in different instantiations being worked on. And then we have this whole question about how does it work? So that's what we're going to talk about today, is a little bit of a glimpse of how it's working in our lab so that we can demonstrate to customers that, okay, we're moving beyond the vaporware and the slideware and stuff like that into the real deal. So I'm going to turn it over to Mayur Shetty, who's one of our systems architects and engineers. Oh, before I do that, some of the early data that we captured, this is a segue into building a better mousetrap, so to speak, for benchmarking, is from CosBench. So this is data that we gathered with a kinetic system running under Swift, same exact setup. So a conventional system with 3 chassis, so it's about 180 drives, conventional with Seagate, that's our code word from Akara, it's a nearline drive, 7200, both 4 terabytes. And so on the left-hand side of this graph, you'll see the read data, and on the right-hand side, you see the write data. So essentially what we get is, generally speaking, there's still some weird anomalies in here, is the read data on kinetic drives or kinetic systems, because it's the whole stack, right? So kinetic systems seem to be better, not seem to be, are better, mostly in the larger object sizes on reads, and then they're a little bit slower on the writes, kind of in the, but we've since made some improvements, so we think the writes are about right in the same category. So for most of our customers are going, okay, so it's basically in the ballpark of traditional systems, but it costs less. So that becomes part of the value proposition. But there's still a lot of work to do relative to make sure that you're going to balance the system toward your specific workload and needs. And that's where I want to turn the ball over to, oh, and this is just the associated data on those reads and writes relative to response time. So it pretty much mirrors the, you know, it's pretty much related. What's that?
Well, that's 16 or 19.
16 or 19. Oh, it just, the numbers there just represent blue and red, basically. It's the run number. It doesn't have any meaning relative to it.
It's basically the runs, the multiple runs, and that's, I think we should have.
How many drives is this?
180 drives in each system.
180.
180. Okay, so
There's a question.
Just to make sure I'm quite getting this. Akara, you said, is an intro code name for a nearline drive?
it's a nearline 7200 RPM Seagate drive. It's currently shipping on the market.
So you're comparing response time for a direct attached drive versus network attached drive?
At the object storage level. So we're not, you know, you can't talk to a kinetic drive with iometer. So this is all at the object storage level from SwiftStack. You send a command down through SwiftStack and you look at the response time of the software portion of this.
Would you say then that what we are observing is actually that Swift is very inefficient anyway? So Kinetic actually can catch up to your block devices, because the numbers in megabytes here, they should be actually 10 times bigger if we were running in an efficient.
What I would say is that it's all related to the total stack, right? And so the drive and the software and everything else will play a role. What we're seeing is that we believe that the kinetic products under the specific stack is going to be kind of in the same ballpark. So you know, yes, I would agree that it's just like I mentioned. It's not like you can just hook iometer up to a kinetic drive and measure it the way you can a traditional drive. So you got to change your paradigm a little bit and measure it at the, you know, at a higher level in the system.
So we're not getting more than from a traditional drive, and we're using every time we're using Swift, we're better off with the kinetic map. I would.
You're at least you're in the same ballpark, right?
Okay.
So I mean, for customers, I mean, the first thing is like, look, you know, it's almost kind of weird to compare conventional and kinetic drives, but of course people want to do it. This is what I'm getting today, right? In the first place, in neither case are we stressing either of these drives to their maximum level, right? So you're saying, okay, the workload's coming in, and typically, in this case, for example, your servers are probably going to be the bottleneck based on how efficient the software runs, right? So, and your network provisioning and all that kind of stuff. And you're saying, if I can achieve this on the conventional side, and I can achieve this at the same date on the kinetic side, and I don't need these storage servers in the stack, then yeah, sign me up.
Okay, that makes sense. Thank you.
But I want to get to the important stuff.
When you're running Swift, are they running, Swift running differently on Makara versus?
No, well, yes, Swift on Makara is running traditional Swift.
So on each node, there's the.
And in each on the conventional side, there is in this particular case, there's a chassis, and then each chassis has two integrated object servers, so two Intel-based object servers in the chassis. On the kinetic side, those object servers are gone. At the top of the stack, there are the exact same servers, same CPU, same DRAM, same networking, same.
Sorry, you're trying to get on to your next slide, the performance data, full engineering. Okay. Do you understand, you have to answer in any depth, do you understand why Makara is bad at one data point for its outliers? And it seems like that you're saying.
We don't understand, or I don't understand that, and you know that I was a little sensitive about that same thing too. So no, I mean there are so many different knobs to tune in Swift and so on, and so in this particular case, I don't know that. There's a lot of these runs, and sometimes you'll see the data points blip at different points, but part of that is our determination that we really don't like CosBench. Because it just is more of a workload generator, right? It's going to just dump all this stuff on the drives, and it's going to stress things, and so you end up, if you dig into the data, a lot of times there's errors in there and stuff. It keeps going with the workload. So what we're going to do now is talk about a system that we developed at Seagate called knobs, which basically allows us to tune a workload and then figure out where you start stressing your system and where you're stressing it. Are you stressing it at the CPU level? Are you stressing it at the network level? Are you stressing it at the drive level? So that it becomes a more meaningful benchmark, so that you can determine, you know, whether or not your actual workload is likely to work on a particular system. Gosh, I didn't think I talked that long.
This on? Can you hear me?
Yeah, you need to turn it on.
You want me to run that?
So everyone here is familiar with Swift, I suppose. Or let me ask this question: who's not familiar with traditional Swift? Everyone's familiar. Okay, great. So this particular setup is something very familiar to you guys. You have the proxy nodes, and then it basically is the gateway or to all the clients. And from then on, you have the data nodes, which are attached to JBods. And you create your object rings in Swift using the IP address of the data nodes and the mount points of the file systems. What I want to point out is conventional and kinetic systems are very similar in a lot of ways, but there's one big difference. The difference is that we eliminated the data nodes. We eliminated the data nodes completely. So now we have a Parco, which is an x86 server that contains the proxies, the containers, the accounts, and the objects, all in this one x86 server. They are then connected to via Ethernet or to the chassis, to the kinetic chassis. So as I mentioned earlier, in a traditional cluster, the ring is created using the x86 IP addresses and the mount points. In a kinetic deployment, the ring is created using the IP addresses of the kinetic drives and the port numbers. So for all other purposes, it's exactly similar. So for example, if you have 3 parcors that you're going to be using, you're going to be creating the ring and then copying the same exact object ring onto those various parcors that you're deploying. In terms of the account ring and the container ring, that's exactly same as the convention. The accounts in the containers are taken care by SQLite database in the traditional deployment. And that's the same in a kinetic deployment. So those will be on your SSDs if you're using SSDs for them, and your rings will be created exactly similar to your traditional deployment. So, any questions on this slide? Or any questions on the kinetic deployment of Swift so far? Okay. So from preparing a cluster, I'll talk about preparing a cluster from a kinetic Swift point of view. One of the main things that we'd like to lay stress on, there's nothing different in terms of networking that needs to be done for a kinetic Swift deployment. Your networking will be exactly the same as your traditional deployment. From a storage point of view, we're going to be removing the data nodes, and now your JBODs, which you had in your traditional deployments, will be replaced by kinetic chassis. These chassis, we work with various hardware vendors or partners. One of them makes a 60 drive chassis, a 4U60 drive chassis. And each drive is a 4 terabyte drive. And each drive has 2 1GB ports. In terms of Swift, we have made the required changes to Swift to understand kinetic. So you can get the source to that from GitHub. It's all open source. You can also use this guide, this deployment guide, to download kinetic Swift and all the other requirements that you would need to deploy kinetic Swift with a kinetic chassis. So these are pretty standard goals that any benchmark or any proof of concept would start off with. Think of capacity and throughput. Mainly what I've seen is when people compare traditional and kinetic, what they would do is they would just take their existing workload from current deployment and then run it against a kinetic cluster. I would say take a step back, start off with what capacity you're looking for from a kinetic deployment, kind of throughput that you're expecting from that particular system, and the object sizes. These are the things that will help you start benchmarking kinetic deployment. So the number of options in terms of tools to benchmark Swift in general. David presented slides about cost bench. We also have HP Scapegoat, which is a very good tool to benchmark Swift. Also, we have Swift Bench and SS Bench, which come along with Swift. It's again open source. But what we have come up with, which is knobs, which is very storage specific and will help you understand your storage system very well, particularly a kinetic system. Knobs, again, is open sourced. It replicates the kind of workload generated by the internet, meaning number of multiple users accessing a storage system or a kinetic system, or a kinetic Swift system to be precise. So knobs, again, as I said, is an open source tool. You can get the source from GitHub. The tool itself consists of a script which it's all written in Python to begin with to create writes to output operations. What you can control is the rate at which your objects come in. You can also specify your object size, starting from a few kilobytes to megabytes. Also, you can specify the number of operations you would like to see. Once you have your write operations, the knobs generates a timestamp.knobs file, which you can pass on to the read script, and also vary the rate at which you want your reads to be done. Also, there's a script which generates graphs at the end of the run. Let me just walk you through this system that we had set up in our lab to demonstrate some of the features of knobs and get some numbers. Out here we have two Parquet servers. These were both running Ubuntu 14.04. We have each Parquet had one or two 10 NICs. One was the outward facing or client NIC, and 110 was the inward-facing NIC to its cluster. On the Sanmina, or the chassis, the 4U chassis with 16 drives, we have two I/O modules. Each I/O module has two 10 ports. For this particular deployment, what we did was we used one 10 port from each of the I/O modules. So what this gives, using each 10 port from one of the I/O modules, gives us a bandwidth of 2.5 gigabytes per second. So from a chassis perspective, we're looking at 2.5, theoretical maximum is 2.5 gigabytes per second. Another way to use it is you could use both the ports from each of the I/O modules, and then bond them, and then have two bonded channels coming from each of the I/O modules. That's another way you could configure your the chassis. So again, what this shows is basically a balanced system from your Swift Parquet, so the proxies. You have two 10 ports coming to the cluster, to the storage, and on the storage side, you have two 10 ports on the chassis receiving it. So let's just try to understand the system a little better. Each kinetic drive can give, a single drive can deliver 50 megabytes per second for reads as well as writes. So with 16 drives in the chassis, we're looking at 3 gigabytes per second. So let's start with the drive utilization. Let's look at like the first column. By just utilizing 25%, making the drives 25% utilized, for that we would need to drive it at around 750 megabytes per second, which means each of the Parquets that we have should be, or the benchmark should be driving it at 250 megabytes per second. Because what we're talking about is replication. Swift does replication of data 3 times. So if the benchmark is driving it at 250, from a storage point of view, we'll be getting around 750 megabytes per second. In our case, we're using 2 Parquets. So each Parquet or each benchmark or the application will be driving at 125 megabytes per second. From a network utilization, from the proxy point of view, the Parquet point of view, which has 110 NIC, for the first row, for the 25%, it's 10%. So we're not really saturating on the host or the proxy network side. Okay. Any questions so far? So now that we have that model, we know that we are trying to drive the chassis or the drives at 25% utilization. So for that, we saw that we needed 250 megabytes from a chassis point of view, or from the ingress point of view, which means from a chassis point of view, it's 750 megabytes. Knobs allows us to set the rate, as I mentioned earlier. So let's take this example of 8 megabyte objects. What we can do is, by driving or setting the rate at 31.25, we can generate per knob instance 250 megabytes per second. So now, when we use knobs to basically create 250 megabytes per second from a proxy point of view, we create 2 instances of knobs running on each of the proxies, and each one driving at a rate of half of 31.25. So what we see is the throughput that we delivered. We sent in 250 megabytes. We're getting around 234 megabytes per second. Again, you should remember that we have to multiply by this by 3, because from a storage perspective, the data replication from Swift is done, which is 3 times what is being sent in. Similarly, for reads, we could use the same file which was created by knobs after the write was completed for the read operations. Again, we can vary the rates to generate various throughputs that we want to deliver and the various stress we want to lay on your cluster. Any particular questions on these numbers?
Yeah. The milliseconds there. Isn't this particularly slow?
From what we've observed is, for this particular one, no, not really. I would say this is exactly what we would get in a convention. We have the same kind of.
I would expect 10 milliseconds, or 50, 500.
System level.
Yeah, are you talking about driving at the drive level, or are you talking about from a Swift point of view?
Application point of view, yeah. Well, if it's Swift,
no, from an application point of view, we're talking.
Like the latency there seems a little bit higher for me than I would expect in a system where you're pushing like block storage, for example.
So then what you were saying, his latency point of view was from the object server, benchmarking the drive in particular, not from a Swift application point of view. So this is from a Swift or a knobs point of view, or an application point of view.
That's the latency to reroll our lock.
Yeah. Or putting the object, basically. Yeah. So we'll come up with a white paper for this, and we'll publish all this in much more details. So look out for that, or reach out to me if you have any questions, or David. There's a whole bunch of information on this at developers.seagate.com. You can download Kinetic Swift as well as the knobs tool. Again, the knobs tool is agnostic to Kinetic Swift or Swift. You can use it with your traditional Swift deployment. Also, it's not Kinetic Swift. That's it from me. If anyone has any questions, thank you.
Thank you. Thank you, David and Mayor. Before I forget, I would like to thank Michael here, taking notes and making sure that people on the web can also watch and hear us. So, round of applause for Michael. All right, next session is the combined certification with the certification team. So I think we can have a few minutes break if you want to take time.
Mark?
Sure. Uh-huh. Absolutely. You have a card? Yeah, absolutely. Oh, thanks. Thanks. I'll take care of it. Sure. I enjoyed talking to you. I'm a friend of Toshiba. Nice to meet you too. Shake your hand, get your card. I'll tell you we should talk sometime. I'd love to. I don't mind marketing. I spoke to some people. I'm actually down there. Okay. Down there. So you're up here? I'm down. Oh, you're down there. Oh.
So what do you do to stop it?
I just turn off the video, turn off the...
Oh, you just pause it?
Well, no, it's not pause it, it's shut it off. Well, shut off the video.
So 1 hour certification, the document, and 8 months, and 2 more presentations. Some more,
Yeah.
So, no, that goes to money. Oh. Oh.
So just stick to this video.
So 3 more.
Yeah.
But we moved, shifted half an hour. So the access was switched it. And we already had an edit. So we are 3. For 30 minutes, sure. No, 4. Next one starts at 3 to 47. Yeah. Then 4 to 4:30. 4:35. Yeah. So where's those mornings? Mornings I'll show and no. That's why the presentation's going to start again. No, I think 3:30.
Oh, okay. Then kind of just...
No, 4 presentations.
Hey, we are ready for certification. Yeah, yeah, sitting right in the front. You want to stand there? Take one of the mics and front. Hey, you know we shifted 30 minutes? So 2 to 3, I'm sorry, 3 to 4 certifications, which have 10 minutes of it already. Then is, when I come up here. Yes, yes, exactly. Yeah. Thank you. All right, Tao is here. Tao, come here. And Sarah is here. Tao, we need you here. Certification. So, let's get started. Where is Paul? All right. Thank you. All right. So let's start at least this certification section. That's a long time we want to do this, but for some or other reason we couldn't. So the whole purpose is to kick off the certification, review the main points of the document that we are going to cover, and then following this section, we would like to follow up with the more details in our monthly calls. Okay? So, Tao, go ahead and introduce yourself, please. First, let's go through.
I'm Towns.
Oh, here we go.
At Michael Travel.
So, I told you.
My name is Tom Williams. I am from Facebook. I've been working on Facebook for the past 5 years. I will helping with the OCP Foundation to enjoy the OCP labs. We have 3 OCP labs set up already. 1 E3 and UTSA up and running a year and a half ago. The third one will be Tsinghua University in Beijing. Actually, Professor Wei is here. He will be director of the lab. So we have the first server test plan was created by the group. The second one is storage, but the storage is kind of more complicated because it involves with all the interface. But we have the storage version 0.09 from E3 lab created. Then E3 lab were too busy. We gave it to UTSA, took over. And 2 days, we're going to spend 1 hour to go over the table contents of topic. What are we going to test? So we are looking for your feedback and comment so that we can complete the test plan.
Yeah, and this will be ongoing, so it's not only today. We need your participation later on through the calls that we have monthly, complete the document, but at least we will have a start today. So Paul, would you introduce?
Sure. So, Paul Rack, I'm with the, as Askar and Al mentioned, I'm with the UTSA lab, Cloud and Big Data Lab. So I think we started almost a year ago. It was around May time frame that we had a big conference, and I see some familiar faces attended that conference. That we started with the first server certification. I think it was the decathlete and the Roadrunner certification. Then recently we worked towards very closely with the storage team and the networking. We just finished the network certification for UNI, for all the UNI certification that you will basically the installer of the network OS, which you will hear about it, I believe, sometimes tomorrow. And now, working closely with E3 as well as a storage group to see what we could do on the storage side.
I'm Xiong from E3. Yes, actually. Yes. And we have established a certification lab, and we have completed the server certification. We define the server certification spec, and we contribute the test case. And last year, we also worked on the storage spec. However, just Tao said that we just too busy and actually at this point 2 version. Yes. And then maybe do TSA work on the storage, and maybe we can discuss the spirit of the certification, how we can make the storage certification happen. Yes.
Great. So the certification document, the link, you guys have all access to that. I hope you had a chance to download it and read through that. It has basically these topics. So besides the summary and license and reference, these are the topics that are usually in every document. But what more is interesting, I think, for us, starts from certification, principles, and and going down that path. But what we thought, talking with Thao, we thought because of the time limitation today, about an hour, we would be better off to talk about the structure of the document. What are the highest topics that we want to see in the document to be covered? So right now I put them here. So if you go down, again, these are the first items. Usually you have these license glossary, etc. But what it starts with certification principles, and then it continues with specification requirements, and then we have these. First of all, the structure of document is starting with specification requirements. You have SRs, and SRs are numbered 0, 1, 2, and so on. And then we have certification specifications. Again, these are named appropriately CS, so that you know these when you are referring to the document CS 02001, you know you're talking about the certification specification. and so on. So before I go forward, first let me go back to the very first list. This is the highest level of topics we are covering in the document. And I hope for those who have had a chance to review the document, any suggestions about the highest level of what we should cover. In other words, we are talking about here certification principles, how we are doing the certification. We are talking the next item much more in detail specifications. What are the requirements to do the certification of the storage? Certification specs, test cases. So what kind of tests we are doing on each and every level of testing? Test case, how the test sequence, execution sequence. So how we do follow, and what are the equipment requirements, and then of course some examples in a document. We think at the end it's good to have we have in this particular document short version and long version of the certification test results. But before we move on, I would like to spend some time to have your ideas about these topics. What do you think we are missing here? Should we add, modify? And I know Per is waiting to jump in. I can read from his face before to add to this. So Per, go ahead.
So a general high-level point is, as the document is written today, it already assumes that you have a known topology and a known set of drives and a known set of applications. And that is actually exactly opposite of what we require. We require a document that will let us do things like bring in an unknown type, i.e. Ashgar has been pushing the idea that I'm going to now have to understand what a 02H drive is going to do for me. And that's not going to allow me to do a RAID group, right? I can't put RAID on top of SMR. That's just ridiculous. So some of the tests cases need to be brought in from a use case point of view. And so to take a use case, we need to know things like topology discovery. The way that topology is done in here today, it actually specifically states that you will be doing star wiring as we designed for Facebook. Well, what if somebody comes along and does cascade wiring? That's going to be a very different thing. What if somebody were to take out one of those hard drives and drop in, say, a 12 gig SSD? Now my topology is extremely important because I can get starvation up on the SAS expander. So there's a whole bunch of problems on what the use cases are. So we almost need to start, before talking about a document, about what is going to happen when we bring in new product, i.e. somebody's going to say, hi, I'd like to put a new thing into Open Compute. You've never seen it before. What are the cases that it's pointed at? Is this thing going to work for databases? Does this thing have HA? Right? We don't even have a section in there for testing the B side card. And we don't even specify that when you walk through the data center, if the card is in the B side, the numbering is different. And so if you go and walk the data center and you go, I am supposed to replace drive 5, you have to know drive 5 of a card that is in the A slot. Again, right? So higher level things are just missing. So that's what I wanted the workshop to be about.
Okay, and there are very good points, Per. Thanks. I think that's the whole purpose of starting this session. My understanding is that we are putting a foundation for storage certification. So with the designs coming in, most famous one, OpenVault, based on that, which Per, you were involved in that, based on that solution, we are deciding to have some kind of basic structure how we do approach when somebody contributes a storage solution to us. Do we test the basic functionalities, or do we test all the varieties of possible configurations?
Let me just say it in a fully politically charged way that I'm so great at.
Mm-hmm.
Are we only going to test Facebook use cases, or are we going to test the capabilities of the device? I.e., do you even know that there's encryption management tools built into Knox? OpenVault?
Yeah. So that's a very good point. Again, this session is for just deciding on that. These are all suggestions. By the way, the document comes from.
So this document is from version 1.
Yeah.
I have no other storage product contribute from outside Facebook.
Correct.
I use this NOx as is my first preliminary test plans. We are looking for help from communities.
And I think that
you the first one, I will call you. So let's work on the new stuff.
I want the capabilities to be documented, right? So the fact that I've got HA capabilities, that I can do Oracle rack instance on Knox is rather important to me. I don't think that the web scale guys want rack, but
well,
adoption.
I can give you my 2 cents. My understanding was, and still is, that when a contribution is offered to OCP, to the storage committee, we need to read through the specs and see what is this contribution doing, what is it designed to do. And based on that, we have to have a test scenario certification to test if what this guy is saying that this contribution is going to do matches in reality what it really does. So in other words, if it says my storage works in an ambient data center with this temperature, so we should test that temperature. Say, okay, it matches, so we check that. So basic tests. Of course, you can take the Knox box in this case, for instance, and add other stuff on it and try to implement it in another environment with a very specific use case. I don't think the basic document should cover that. I think the basic document should really cover only what is in the specs of each contribution. And if somebody takes it and uses it in special cases, and that's great, we can document it later as an appendix or whatever, because this is going to be a living document. But at least at the basic level, we need some structure. We need to say, okay, for instance, Per, what would you suggest to change the order of topics? And these topics are what is already in the document we are going to review. For instance, what are the certification principles? Because what I heard from you is more talk about the certification principles, and we can word it and discuss it, but that will fit in that category. But before we go deep into that level, is there anything else you want to change? Is there anything you want to add on? And if you are on the mailing list, I sent several emails saying, please download, please read this document and come prepared. But if you haven't, that's okay. We summarized it here. Is there anything you want to add to this?
I have a question, actually.
Yeah.
Who is the ultimate reader of the certification? Let's say I have something in a box, I bring it, we certify it, we add it to the list of certified solutions. Who is the consumer of the certification?
That's a very good, and I will let Tao answer, but I give you my point. See, part of the certification is interoperability. So if you are coming with a new solution to the OCP, because we are testing the very first contribution to the OCP storage was what? Knox box, right? So we are building on top of that. And if you are coming and let's say your storage claims that I work with any other OCP gear, one of the tests is to see if it's interoperable with Knox box, if it can talk to this guy, or if it can talk to Winterfell, because there are still approved and certified solutions with it. So we build on top of that. Once we do that, we have to check, okay, what more additions you're doing, right? What new features you're adding to your solution.
My question was more like, who cares? Like,
no, the certification, because
Facebook cares, Tao is happy. Who else is happy?
That goes into the need for certification. Why we have certification?
We do care.
We do
care. Right? Knox is designed to not only service Facebook, but was designed to be able to service things like the Microsoft clusters, right? A and B takeovers. It was designed to be able to do OLTP kind of things. It was designed to work as kind of a Clarion replacement for the bigger type of, I want to do a lot of work. My question back to this group is, do we care, right? You're asking who cares, and my first question is, do we care? If we don't need to certify it, we just let the people make claims, and we certify what a consumer actually uses. In this case, Facebook doesn't use any of the self-encrypting capabilities, key management, doesn't use any of the HA. In fact, of the 11 claims that I made when I first built this thing, there's only 2 actually in use. The fact that you can hot swap a drive and so what features do we want to know? Do we, like, if you read all the claims on this thing, it's great.
right? This box solves the bread slicer problem. But do you want to see that in the certification or not?
Well, I've got a question on this. Does the certification have allegiance to the physical hardware, in this case a Knox box, or does it have more allegiance to the use case? You know, as in Facebook use case, or possibly, could we have a dozen certification documents for one particular physical instance?
These certification plans were based on not, but this is JBOD. So any JBOD device can apply, can use these test plans.
Today, most of the certifications are for other work groups. They are more system, basically testing. But I see your point. I've done, especially on the storage side. If the community thinks, the box as a system is solid, I think today that data is just exploding. People, they are more curious about the use cases. So if the community feels like we are at the basically good level of system testing, I think it makes even the life for the lab, easier, that we move up the stack, which is the solution use cases, and we look at, simple big data analytics. Everyone's talking about it. Hadoop, SAF will set up those environments and kind of, it's a different type of testing. It's a lot of optimization. It's a lot of configuration to get the best performance number out and best, layout. But, that's assuming you do those type of solution testing or use cases if you think your components are in good shape. If the community thinks, the system testing is not, I think from the certification, it's really up to us. Start maybe going up the stack to look at those use cases, because that's really where customers, they want to know how to set up an optimal Hadoop or SAF or XYZ.
Can I have one other mic? You and then.
I was hoping that the answer to who cares was a little bit of a simpler answer. The answer should be the consumer. The consumer is the one that should care. My thought was that the consumer wants to see basic interoperability. And it's not between a server and the storage JBot, it's between a controller and the JBot too, right? And as a consumer, that's what I would want to know. I would want to know that this JBot functions. I would want to know that if I plug in certain controllers, I want to know what controllers I can attach to it.
Yep.
Not necessarily whether it's in a Winterfell server or some other server. I want to know the controller attaches and functions with JBot. You move up stack, into the solution test. That's great. But I would want to then it gets more complex, because you're going to have to go characterize which set of solutions have large volume on them. Who cares? Becomes a little bit more important than in terms of what solution you apply it to. The thing is everybody's configuration for a particular solution, even if you pick Hadoop, is going to be perhaps slightly different. And so you got to be a little bit careful when you start to move up stack, right? I would want in this testing, I would want to see interoperability. I would want to see the controllers and JBot functions. And the other thing, I heard somebody mention temperature and some of the environmentals earlier. A bunch of you guys are going to have test labs that are going to be cycling temperature while they're performing tests, which gets complex and expensive. I mean, you're going to do shock and buy too. I think that you want to have people validating that, the company designing the JBot validate that in their own environment.
And that's why I meant by system test, really the basically at the system level, which is the controller and the basically enclosure. But the question that you brought was more on the use cases, which is slightly different from the system test.
It's okay to do this full solution test. That encouraged and good probably to that you performance issues and other things pop up in that kind of environment, but I would separate the two.
So to answer your question,
testing and interoperability and solution testing. Separate.
Yes, two different.
So it's two different certification. Only test at normal condition, room temperature. We don't do any temperature test or shock and fire, any environmental test. Only room temperature and standard condition. So this is for, at current, the setup we have JBot testing with one controller. We know that the HBA or array controller card from LSI is work we use that as a test picture to test our JBot. we are not doing kind of incompatibility test with other HBA, other vendor. That will be more in the one other company like Advanced Labs. They do the component qualified level, so they can test the component, the controller with the different host adapter card, operating controller card. For us, with the lab, we only use test unit under test is storage, JBOD. We do rewrite, transfer. We do 24 power we idle to check all the basic functional tests. And
Unfortunately, though, all controllers are not created equal, and even though we have this super tight, thing of a spec called the SAS spec, we all know that there are issues that crop up. So it would be nice if there were more than one controller, fault testing.
Go ahead. Ma'am, takes a little minute to explain the structure, and maybe I would like to answer the use case. Yes, and for me, for the certification, I just give a presentation in the certification section. The first thing that we need to set the certification baseline. So that is the document. So basically, it consists with the why you test this and what you will test and how we do that. So why you test this, basically it will come from the OCP spec. So for the storage certification spec, it should mention the OCP storage spec. So for me, just for the use case, actually I like the hardware management spec most. If you have time, you can check the hardware management spec. They come from the use case. So they will explain their use case and they will set their requirement. So it's said very clearly. So basically, from this OCP hardware management spec, we will know very clearly for the use case and for the requirement. So from this, we will answer why we check this very clearly. So basically, if we have this kind of spec, also something like OCP server storage spec, and they come from the use case, then we will know why we check this. So for the first thing, it will come from the spec requirement. If we have the use case, and then we have the spec requirement, we can put it in this section, and then we can write our perception and what we will check. So based on the requirement, we will write down our requirement, spec requirement, certification requirement, and then we come out the test case. So so for me, it's better if we can come out some use case in the storage spec, and we can answer the use case so that we will have better structure. And actually, for this kind of test, mostly it is focused on the NUX, on the JBOD, and have some test case cover from the system, from the controller, and from the server point of view. So it's just a little bit of explanation on the structure.
So we have a question here.
So maybe my question has to do with one thing you had up here before, which is called certification principles. With all this discussion, I apologize if you read this. I don't have too much of the background on what you're doing in the other ones, the other certification group. But in the past, I've walked through other summits where there may be a company like Hive or something like that who says they'll have a little sticker on their Winterfell chassis or on the blade that goes into it that says certified. And I asked myself the question, what does that mean? And in the context, and I'm not exactly sure that I do know that, except for the fact that if I have a Winterfell chassis, just a cheat node, and if I got 3 certified blades from 3 different companies, I could plug that in, and they would all work, because it was built to the spec. I'm assuming that's the exact same thing you're trying to do. Correct. So if I have a Knox chassis, which is, sorry, that is Open Vault? Open Vault is the official name. Okay, so if I have Open Vault, all that means to me is that it's a JBOD that should be built to the spec that Open Computers do. And why does it have, what is the extra complication that you're adding here with interoperability except to say that it works with SAS?
Well, the certification first, your first point is exactly what you mentioned, that the consumer later on, because all these specs are available to download down to Gerber files, down to the CAD files. So if a company X comes, downloads everything and starts building it, right? The consumer at the end of the day needs to understand if this really matches what is described as a open vault solution.
And that's the number one principle.
That's the principle.
Is that the number one principle that's written in your document? Shouldn't it be? And that is the number one principle. That here's a spec released by the incubation committee. Are you building to that spec or are you not? What do you need to do that? I don't care how simple or complicated it is. Are you able to do that? And that should be the number one principle. Is that the principle that's written there?
I believe that is our goal. That I don't know about because this is not there, but it is our goal to make it that way.
I think what James has just said can be twisted a little. To be twisted a little and say paraphrase. There we go. What we're really talking about is aiding anybody who wants to put it on their HCL to know that it has already gone through base testing, signal quality, all the things that the vendor who built the thing should have done, right? It should have been shake and baked. It should have been all of these things. They should provide those documents, preferably. And then I, Oracle, want to put it on my HCL, so I can say, I can look at these specs, I can look at the testing results that were given with it, and I can say, that's valid for me to start my testing on. Is that a fair paraphrase? Or, yeah. How many people want that as the level that we're working towards? 1, 2, 3. How many people are totally off base? How many don't want to vote at all?
We also want to know that and I think this
we
is
really
what you're
need
saying,
mics.
So I just want to check.
For the removed guys.
Storage is about data. I mean, right, you're the data business, so we want to know that you can plug some controller in. The way that we check, ultimately we're assuming at the hardware level somebody's done all the signal integrity and all that underneath, right? But the way we test that is we've got to plug a controller to it, we've got to move a lot of data back and forth to it, potentially manage it in some certain ways, and that's what you mean by compliance with the spec, right? I want to make sure, because I want to know that you can move data back and forth from a controller.
Well, so there's a difference between I go and buy a PMC controller from Best Buy to I go to Quanta and say, here's these Gerber files, build it. And that's the real twist that we've got here, is we've left the OEM market and entered the ODM market. And the question really is, do we need to certify down to signal integrity?
You want to see this thing run at the equivalent of the UNH ILO?
Yeah, I don't, or let me go back and answer this question first. I'm assuming signal integrity is taken care. I'm, again, just backing up and speaking from what I'd like to see from a functional standpoint. I'd like to know that I can move data back and forth to this box at a certain rate, and it is reliably moved in and out of the box.
I wish I had that much faith. Unfortunately, I went through so many red boards that it's ridiculous.
I think if we've got cert labs that are sitting there, running, spice, doing signal integrity at a very deep level, then we've got somebody who's produced the hardware designed initially.
So here, let's say, let me pose this directly to you, right? I just downloaded the Gerbers and I have gone off to
job deal to build it, and they are building me a brand new one. Nobody has ever, they haven't put it through their qualification, right? So they hand it to me. Is that still OCP certified, or do I now hand it to you and say, prove that they did the job right? Or do I need to do signal injection? Where is the base level of everything is working so I can get to the point where I can say mount minus T and go and do IO? Right? I want to know, I want to be at your level.
This is a fair debate because this is bottoms up versus tops down.
Absolutely.
Am I starting to see if I
I want to
move
be where
the
you
bits?
are.
Am I starting to see if I move the bits, and if the bits don't move, then do I stop and kind of back down into what the problem is and do signal integrity testing, or do I start with signal integrity testing? That is the discussion we're having here.
Now,
Question number there.
So, actually, since you use Jabil, and since I'm part of it, my friends, this is an interesting point. For those of you in the CNI, I think this is a follow-on to the discussion we were having in the CNI committee, which is we don't have a good handle on where responsibility lies for various parts. Speaking as a solution provider type person, if I went out and took someone else's group, spun boards and built it, I would be responsible for, I put my name on it, I'm responsible for what it does. And so I'm going to do stuff in-house before it ever gets to E-Tree or UTSA or wherever it's going. If I don't do that, I don't deserve to be building this. Now, so I think you have to look at whose responsibility. There's a chain here. If I'm selling this finished system to somebody, and I've tested it, it works and all of that, but someone puts shingle drives in it, which change the whole characteristics. If I ship it with the shingle drives, I'm responsible. If they add it in later on and it's not part of what I told them it would do, they're responsible. I mean, people should have the ability to screw themselves if they so want to. And we have to make sure that we don't add so much cost on the early parts of the system that none of this ever gets to market. And so we're in a space that's, at the upper end of the price range, you have a few tier one vendors. At the lower end, there's the whole white kind of, and gray and black kind of versions at the bottom. And there are price differences there, and people will get different things depending upon what they're willing to pay for and what kind of risk they're willing to deal with. In storage, you have the issue of that you have a bunch of sockets and you do not know next year what drive or drive-like object someone's going to shove into one of them. You can't in advance decide. I wouldn't have even thought of SMR a few years ago. And now, so you really have to just pick off whose responsibility and do some work to make sure that it's not a complete dog, that you're getting reliable signals going back and forth. I think that's a fair thing at any level. But I'm not going to be checking out every rate controller in the universe to make sure that every one of them works, because God knows I don't think there's anyone that does work right now, and I never get anything done. So there's a limit. You have to be careful to make sure that we can actually sell them.
Is this design validation testing or is it interoperability? It sounds maybe we need to, if it's supposed to be both, maybe that's a great discussion that a smaller group has to go out and have.
You're in charge for sure. Right, nothing moves on. We are talking about this document for how many weeks there now? Months?
Years.
So that's the whole thing. That the reason we put it on the agenda is to engage you guys so that in the future in our monthly calls participate, because each time I send an email, say what do you want to add to the agenda, I suggest something. So please push for this so that we put it on the agenda and say, okay, here is, we can step by step move forward and review all the items that are listed here and add or remove as per ones or you want. So I think this is a great discussion, but we need at a certain time get to work and really make this document happen.
From OCP Foundation, we spend a lot of time to write a test plan. Every time we send a new version, we didn't get feedback from the team.
Yeah.
So we need some feedback.
Here is the mic.
I think I can talk, yeah. Okay, so let me clarify the question that I asked 20 minutes ago. And this was...
You mean we didn't answer it?
No.
Okay.
So I asked who cares, and I got an answer here, the customer, or the client, or the prospect. But who is the prospect? Is there a prospect here who is attending today in this room and is a prospective customer, not a provider of solution of an OCP solution? Facebook is a customer, right? But also you do actually ODM, so you are telling the OCP providers what to build, right? So maybe you should just take the document that if you're happy with it, just tell everybody in the room, well, I'm one prospective customer. Listen to me because this is important for you to be validated on this with this certificate in order for me to be able to even start a proof of concept with my data center with your new technology, right? This I think we would understand. But otherwise, asking us, we're not the actual customer for the end user who will read. Like my question was loaded, right? I think really that we should ask who are the prospective users, ask them what certification they need, because that's what we care to provide us and end user. So if Per here knows that Oracle next door actually needs OCP storage and looking at certain features, he should be gracious enough to maybe to share with everyone here, well, this is the 10 things that Oracle needs from us, and that's what we should do.
So let me address that a little bit differently. I think when you buy a laptop, it says Intel inside. That's a kind of certification that shows you rely on that. Say, okay, this is a box that runs on Intel, right? So when you get a box that says OCP certified, you want to make sure that you get the same reliability, you get the same appearance of the solution that you're buying. You don't want to rely on the end consumer. The end consumer, in my opinion, should have some input. But those who designed the solution and those who are providing, like Jabu maybe, who are providing the solution, have to test it first. Say, okay, this solution is meeting all the requirements that this document provides. Because without this document, you know, with this, you tell somebody one word, at the end of the room, you hear another word. You know how it is, right? Again. So if there's no standard, everything will change on the fly. So we need a standard to make sure that every contribution that comes in meets that standard. Of course, each system builder will do it in-house, but at the end of the day, before you get a stamp that says, you know, OCP certified, you want to make sure that somebody looks at it. Actually, that's in advantage and interest of the customers, right?
So you're arguing that our certification will be for a particular use case. In the case of Mike says, this thing works for type 4s and type 5s. Then if he comes up and starts building type 7, he has to provide another document or a revision to this document to say, this is how it's designed in cold storage. If you cable it wrong, you're never going to know. If you put in the wrong type of drives, it's outside of scope. So this is a NOR document rather than an XOR document, right?
Well,
so
whatever the specification.
But the real point that I want to try and get to is, are we trying to help adoption? Is this document going to make it so that Atmos says, I want to replace my JBODs behind my object store with these JBODs instead? I see this document as a leader to, hey, technical validation, this is a good box to replace my existing solution or for me to build a solution on.
Well, I'm not so sure that it's necessarily a good box. It's just that I went off and I read, I went off and I read the spec for OpenVault. I like it. I want that. I want to work with a vendor who makes this, that I am assured that they built it to that spec. That's how this certification tells me that. That's number one. Number two would be, will it interoperate with standard interfaces and the like? as interoperability part. That would be part B. That's what I'm looking for.
And I believe you summarized it very well.
By me that I like that
Because
particular
I think you summarized it very well. That's the whole thing, that when somebody, again, contributes a solution to OCP and you can go and download all the Gerber files, all the specs, diagrams, and build your own, how a customer can make sure that this design meets the specification that is approved, reviewed, and approved by OCP, right? That way, this document helps, and the tasks that V3 and UTSA are doing helps basically to achieve that goal. That when you buy that stuff, with that sign on it says OCP certified, meaning that meets those standards. That's the whole point, I think, behind this document and what we are doing here.
But if I'm hearing E3 correctly, it's the interoperability portion that you're willing to stand up, well, you and UTSA are willing to stand up and say, that's what we do. We're left on our own to know what kind of RV, signal, etc. we should be trying to get our ODMs to actually build to.
Again, I think it's based on the certification should be based on what is the contribution specs are claiming. So if your contribution says this and this and this feature are included in this storage box, then the certification should make sure that you really make those points working for your solution and approve it. If not, then you have to work on it. It's not only interoperability, but meeting the specs.
Do we need to split this into two documents then?
The specs would be the wrong word, shouldn't it be standard?
Well, that would become then later on OCP storage standard for this particular solution, right? But I think we shouldn't make it that complex. There is a solution with certain specification within OCP, contributed to OCP, and the customers want to understand if this certificate if this product meets those claims. Who certified? Who tells me that this meets those claims? OCP certification. So you should go through a test and make sure that it meets those. And then the next step is the interoperability. If I have older version of, let's say, a server or a controller, does it work with my storage? That would be the next step, interoperability. But I think the first goal, as far as I understood, is to make sure that the specs, and Tal can chime in here, the specs are met. In other words, we test to see if you are building something that the specification describes is part of the solution that is provided.
Yeah, Aska is correct. This test is we wrote the test plan based on the test spec from Knox, Facebook Knox. So our goal is to meet the spec when we test it. So if we want to do more than that, we need.
And of course, you can add it. Yeah.
Yeah, we need community here. This is including flash storage vendor. We haven't discussed about flash storage vendor. Digital, maybe I know that we are missing flash storage, so
and
that's next to be discussed.
Last question with that, because we have to wrap up just before we go to the last comment or question. You see how difficult it is to run it. So we are spending 1 hour just to make sure that if it is useful to do this.
The CNI committee has been doing this for 3.5 years now, and we don't have an answer. So, but there's a few comments I'd say. First of all, most of the OCP specs are not testable too. They are incomplete, inconsistent, and they are not updated enough. So if that's your goal of testing to the spec, you're screwed to begin with. That's number one. Second, your point about the Intel inside, it doesn't tell me the system works. It tells me that Intel's giving the company a kickback for putting the label on. That's all. So you got to be careful about what we're dealing with. You know, for the most part. So guys like Facebook, Rackspace, they're working directly with the entire infrastructure, and they're talking to the vendors and the part makers and all of that. But most people who are buying equipment, they go to a solution provider, and they come to us and say, I want a system, it needs to do this. And then we, supplying that system, we're the ones who guarantee that that system works. So in some sense, the testing is for me, so that I can make a choice. Right now, no one has ever not used OCP because they said, I don't think this is tested well enough. That is never a question I've ever heard in any meeting I've had with customers of any size. And that's because they assume, oh, this is what Facebook's using, I don't have to worry about it anymore. They've already cleaned it up. Or this is what Microsoft is using.
Part of it is because the vendors, the system builders are only few right now. But as it grows, you know, you have Vivian and Quanta. Of course, they build the same thing for everybody. But if you have now, 2 years from now, 5 companies making hardware, how you want to distinguish between these?
Right. What I'm saying is, I'm the one for most of these guys who's going to have to make that decision for them. Right? I'm going to go out there and they're going to come to me and they want a solution. I'm going to say, you know, I want you to use the Quanta server with the stack velocity drive system.
You're making the argument that since 50% of the bytes shipped go to only 5 accounts, those 5 accounts can deal with managing it themselves. Everybody else should come.
Not that they can, they will no matter what we do. There is no way Facebook's going to let something into their data center that they don't have 500 people who've played with it first. It's just the way it is. So we should be worried about the other people who don't have 500 engineers, but that we need to start buying those from.
Exactly. And with that note, I would like to thank you everybody for participating in this discussion. I think that taking away message is really please participate in the monthly calls to wrap up. Will take a long time, but wrap up with this certification document. So with that, we have our next presenter. Did you send your presentation to me?
No, I didn't.
No? Okay, then you need to come in and hook up.
Yeah. Is it me? I was consulted.
Yeah, we had some change of schedule.
Yeah, only some.
Many slides. I need an hour.
You have a HDMI or
I think it was
You looking at that? Oh my God. Okay. Okay. So for those of you who haven't, thank you, Robert. Now it's better. For those of you who haven't met me before, my name is Dimitar Boyn, and I represent IO Switch Technologies here. Some of you I have seen last year in May, really, in Texas, where I started touching on the topic of switch fabrics in storage, and especially in the big data center context. And today I will take your attention, ideally, to the problem of where we were during the last 15 years, building storage fabric between appliances, and eventually evolving into a new data center where the storage devices themselves are networked and are communicating between each other, to each other, and a part of one meshed, completely duplex switch fabric. We got actually involved in the OCP movement last year in January through the hackathon. I met a lot of great guys there, and follow up through the following months, trying to capitalize on a few ideas that we had through the hackathon. Ever since I was thinking and couldn't help it, well, funny, what would it be if IT architects actually were designing cars how would cars actually look nowadays if we were not producing computers but cars? And I started reading on this because there were some obvious misconceptions, and here's what I found. So probably we will build cars similar to this one. If anybody has ever wondered if there is a car with 2 engines, probably if we were building them, every car would have 2 engines because we like power supply redundancy, right? Then we would be building something like this excellent Tornado engine, dual engine machine. You can see the specs. I won't read for you. I just want to take your perspective on what we are doing in computer science and what we shouldn't do in cars. And there's probably a reason. You can see that there were engineers around the world who were considering putting 2 engines long time ago, long before we have actually hybrid cars. And it was making sense because the 2 engines were performing completely different tasks for us. And most of the engineering actually went into, instead of doing better power supplies for cars, than putting 2 of them redundantly there, right? And nobody actually went and started installing 5 running tires just because we want rate 5 redundancy, or having double the number of tires, or like cars with 8 tires, usually are like just trucks because they need to load more tons per truck, not the redundancy issue, right? So the few guys that I've seen around last May probably remember a similar slide. Back then I was thinking that, well, there is not much difference here, or one out of these guys actually doesn't belong to the slide. Who here actually knows what Piggly Wiggly is doing? It's a grocery store. What are they famous for? Does anybody know? You don't. Okay, just notice that you know enough about EMC and NetApp, and we have a grocery store here. And the question is, where is the connection? What do they have in common? Here's one suggestion that actually I realized a few months ago. Well, they're both general purpose stores. Like, have to do something about the general purpose stores. How does a general purpose store look, and what we sell to enterprise traditionally, because we're like the storage group here? Well, we have a counter, right? And we have a clerk behind the counter. We have a bunch of merchandise that we have to deliver to the clients. And for my explanation here, we have the merchandise is our storage, obviously the data and the data blocks that we are running. And we have a counter where all of our clients are accessing all the merchandise through the software that we have pre-installed in our of the clerk, who is running back and forward to deliver everything for each customer. Well, if you have attempted at least a few of our own storage pitches through the time, you would probably know that we have been promising for about 20 years to all our customers that we are delivering switch fabric. So the great idea about network access storage, object store later, as well as some, was, well, here's this switch fabric where you can actually connect a lot of clients to the same set of data and manage it very dynamically, recombining separate hard drives into logical LANs and achieving storage resource elasticity. This was what we were promising to the world. However, we were promising this as just a lot bigger store. It was just a combination of a mall where we had a lot of general purpose stores. And I have Piggly Wiggly here because what their founder discovered about 100 years ago was that this architecture doesn't scale. It works well for very expensive malls. If you are selling gold or if you are selling diamonds, it works very well. But if you're in the game of selling more pounds of flour, perhaps bottles of oil, if you're in the business of scaling commodity, it doesn't pay well. Why? Because a single clerk can just scale that much. And you, as long as you keep a single clerk in the way of 100, 1,000 clients, the clients will be waiting in queues, and you wouldn't be selling that far enough. So what the Wiggly founder invented was the modern day market, like Safeway. If you've been in Safeway one of these days, you will notice that they even did self-checkouts. So even the security and depositing the money, similar like Amazon does, is all delegated to the actual customer. What we are thinking about now is that a true switch fabric would actually let any client accessing through a switch fabric any of the devices directly. And I would say that even further, any of the devices, because they're on the same fabric, could actually automatically talk to each other too, which we have kind of going out there with kinetic hard drives nowadays. We have the compute unit there, they live on a two-part network switch, so potentially they could actually exchange data without engaging the clerks in the front. Yes. So according to us, we decided about a year ago that everything is wrong with this picture, obviously, because every time I look at this architecture, I'm thinking about having two engines in the car and limiting my SAS HBA adapters, actually limiting the access of my clients to the merchandise that I want to sell to my clients. I'd rather let each of my customers walk out the aisles, get directly the data bits that they want, and get out, self-checking out and leaving me the money without any clerks in the store. I want full automation of getting in and out of the customer. So what we are here actually to show you today is the concept of Open I/O. That's how we call it after we did the adaptive storage hackathon last year, where we demonstrated that it's actually possible to attach any current SAS or SATA drive to a network addition, which will very efficiently, for the additional cost of between, how much is a 1 gig port of Ethernet cost nowadays? Anyone? Like we're hardware guys here. I would guess it costs us like about $1 to add it. So redundant part $2. Let's say we have to sell it to our customer for $5 more. So you get any SATA or SAS drive, you keep its full performance speed, not adding anything. You can connect it. That's what we demonstrated last year at the hackathon, right? So you can then connect each of these drives individually to an Ethernet switch very efficiently, and then let any number of compute nodes actually do what we have been promising to our customers for the last 20 years. We have a true switch fabric where each client can access any of the drives. We can dynamically recombine not only the drives logically behind the counter, but we can actually recombine the compute clusters dynamically, because that's what virtualization let us do. I can run on the same hardware platform any combination of virtual machines, accessing any combinations of data drives behind them, and we can scale the virtualization of our storage pools dynamically. So what I think we have here is actually, this is a lot about Open I/O concept is that we could gain what we lose, and we lose if we lose our HBAs, we will lose the bottleneck of having a counter in our general purpose store and turn it into a supermarket. And in addition, what we will gain is we will no more have a common failure domain. So this will allow us to linearly aggregate the existing IOPS from the separate devices, save on unneeded CPU utilization, and aggregate linearly capacity and bandwidth too. We've already demonstrated this. So we are pretty much embracing what Seagate is doing as concept completely and fully. We have one little addition to this. We have a different perspective, where Seagate is seeing actually the object store and the access method as a common denominator, where we have to support, each drive needs to support the object store API and the Ethernet connectivity at layer 3 of the OSI model. Our group actually proposes that OpenIO keeps only the specification up to the Ethernet here. So what this achieves is that instead of going to manage TCP/IP, we can natively aggregate the existing resources and discover them, keep the down to layer T, to layer 2 a specification, and let the applications actually use the original block target, addressing only through RESTful interface in the sub cases where we really need it. So RESTful is great. We can get together in the lab, do a head-to-head test about which concept actually lands it better, with better scalability with the same resource. I love the comparison that the Seagate guys did today on operability and total cost of ownership, running Swift with normal drives and kinetic drives. Same concepts apply actually if we push a little bit further, and we will see that we can realize all of these savings and push a little bit more on getting even more bandwidth and IOPS with the same stack. So how we did implement this? Well, we built our own version of things, which I actually forget to mention, but so we have developers kits, and we are ready to open this for anybody who is interested to make side-to-side discoveries for themselves. I know that no one professional enough will actually take my word for granted, right? You want to get kinetic drives and kinetic developer chassis, and perhaps 60 drives on some Mina, and run your own tests. So we can help you run smaller tests, not with 60 drives, but a few drives, because the Ethernet obviously scales linearly. What you get from 5 or 12 drives, you will get from 60 drives. We have this easy, implement yourself, 3 minutes, plug in any drive, and you can test actually the difference, how does a Western Digital drive behave compared to Hitachi drive or to a Seagate drive. And also, we have this very convenient, almost like USB drives that you can connect without even opening anything. Just grab it, get a drive, attach it to Ethernet, and here you go. You have a system that actually gives you an Ethernet drive, an Ethernet link. So we went even further. Last year, we were working with the hackathon team here, and we created a demo which was using Hadoop, connecting very small Adaptiva servers to the same Ethernet switch where the Ethernet drives were connected, and we were running Hadoop 24 hours later. Right? And this is actually a picture from our original design, where we were thinking, well, maybe it makes sense that we connect each of the drives directly to a 1 gigabit interface, and that's what we were imagining doing. Well, I actually asked for the customers earlier today when we were doing the discussion, because what we did after that was, well, first we thought maybe it will be easy to go and find one of the sponsors of the hackathon of this event, like Quanta, for example, take their interest in what we have been doing, and they will do a chassis like that because they will love it. Well, it's not how it works. So 2 months later, I was calling all of my acquaintances, VPs, and directors of IT around in the valley, asking them, well, what do you think about this? And what we got as a feedback was too many wires. Do I need to have 15 1 gigabit connections to each of the new Volt chassis? It's kind of too much. Give me something which is better integrated. So I know that unfortunately Supermicro are not part of the OCP yet. They don't have a policy, but we were able to go between working with Seagate, the Kinetic team, and Supermicro supporting the Kinetic concept. Actually, we're able to grab a new concept, which is a lot smaller than what it would take here as of last year. So a year later, we are able to work with switch, which is dual path switch, to 10 gigabit connections on each path, and you connect to 16 drives behind it. With dual path, integrated, so not that many wires, and you achieve actually the same flexibility as you have 16 paths at full duplex at the same time. Next step, about 4 months ago, was, well, who actually wants to work with us? So we went back and forth to Taiwan, and because half of my company is in Taiwan, we were able to establish a targeted concept which implements everything I've been telling you about on the rotating Rust. But yeah, it's not all. We actually work on the flash side too. So taking the same concept, and this is a little bit challenging maybe, we implemented a PCIe switch fabric, which works with Memorite M2 elements. And I know that, I think earlier in the morning was mentioning, somebody will be talking about implementation of M.2 PCIe elements in the Open Compute servers tomorrow at 5:30, if I'm not mistaken. But so we had this vision about a year ago. So we implemented PCIe connected Goldfinger connection card, which works with 4 PCIe M.2 elements. And thanks to our partners at Memorite, we are able to deliver, well, these are the specs there. I won't just read them out, but the interesting part is that, well, it's the same concept as what I was talking about, the Ethernet switching, implemented in microsecond latencies now. And we are able to do directly RDMA configuration. So next step, 3 months from now, you will see whomever is interested about that we will integrate InfiniBand and converge the Ethernet interfaces directly into the switch card, which now can go directly, like the mock-up here that you see is actually a 8-lane Gen 3 PCIe switching between 40 gigabit lanes on the card. So just something to think about. We've already discussed with the Open Compute Storage initiative that we want to deliver as much as possible and give it back to OCP. So we have certain designs which we will actually give to everybody to try to follow us. So that's pretty much it. One simple concept, eliminate edge base, deliver an open fabric where devices can live between, in the space between the switches rather than on the hosts. That's why we need host adapters, because we've attached our storage hard drives to the host. We then attach our SSD or flash to the host. Obviously, the switch fabric that I had here on the picture before that, it talks RDMA and has dual root complexes. So independently of where the switch is, you can connect directly and invisibly and implement PCIe pass-through and RDMA connection from 1, 2, or more hosts this way. Ultra low latencies and linear aggregation of bandwidth and IOPS. That's what I want to kind of give everybody today as an idea and direction of where we should be looking, because this means that we can perhaps catch up with Facebook's fast pace of innovation and the ambitions to be everywhere in everyone's pocket always. We have to enable them somehow with hardware. That was all from me.
Any questions?
I hope you're not completely tired and bored.
Thank you.
I see somebody left. So. Thank you.
So next, are we tired? No. Thank you. Next, we have Jim. I'm opening the schedule here, so. Jim Malina. You have your presentation video, right? Yeah. You want to hook up? Yeah. For those who are still here, the presenters, if you send me your presentation in PDF format, I will publish it in the video.
Hi, my name's Jim, and I'm a device guy. And truth be told, I'm a lazy device guy. So my mission is to give you really cheap storage and to make it as simple as possible. Albert here is my partner in crime. He's on the other side of the wire, and so all of my laziness he has to make up for with his youthful exuberance here. So we're here today to talk to you about shingle magnetic recording by a raise of hands. Has anybody not heard of it? Okay, you guys are prepped. So what we're doing is we're overlapping tracks. Tracks is going to give you better TPI, more capacity, same dollar amount. So some background as to what it takes to do SMR is the tracks are physically going to overlap. We're going to group many overlap tracks into zones. A zone might be hundreds of tracks. So the reality is it's going to take several seconds likely to either read a zone or write a zone. So the question then becomes is who owns the responsibility of this physical overwrite? Is it the device? Is it the host? Or is it both? So this has been discussed quite a bit for several years now. It's gotten to T10, it's gotten out of T10. It's the standards committee. And one of the results of those activities was definition of a host managed device. So with a host managed device, the host is now aware of these zones, and it's aware of the zone types. And so with host managed, we're offering two zone types. One is a conventional zone, where you can randomly access it, just like you do today on today's drives. And the other type of zone is a sequential write-only zone. And so that requires the host to physically write sequentially. If the host does not physically write sequentially, we have a problem. The drive will report an error. Both of these types of zones are statically mapped. The drive not doing any internal read modify writes. When the host puts the data there, it stays there. With host managed, there's new commands. There's commands to report zones and commands to report where the write left off. Another output of the T10 activity was to define something called a host-aware device. And a host-aware device can have the first two types of zones. It also introduces the possibility of having a third type of zone, which is a sequential write-preferred zone. A sequential write-preferred zone is kind of new. What it does is it offers a dynamic mapping capability. The dynamic mapping capability has some resources associated to it. It has some mapping resources. It has some media resources. It has capability to consume resources and capability to replenish resources. The resources are typically, like I said, media, SSD. What the mapping capability does is it effectively blends LBAs to the media. So what's happening is hosts that aren't writing in an SMR-friendly manner, the indirection kicks in and writes them sequentially, but keeps track of where they are. At some point later in time, presumably, those resources get replenished via a read modify write at a zone granularity. Last bullet on the slide talks about out of order writes. So that's really an NCQ comment. So when you introduce in a host-aware device the capability to handle writes that are out of order, there's some question now as to what's the device going to do with it. Is it going to put it into an indirection zone, or is it going to wait because maybe there was some queuing and they will eventually be reordered or come in sequentially ordered? And so there is some ambiguity there in how devices handle it. It's just something to be aware of. So costs of host-aware device. So what gets talked about most frequently is the performance aspect of it. And that's really a repercussion of the time it takes to do a read modify write of a zone. But there's some other costs too. One is the power. The drive's going to be taking more spins to be able to reclaim these resources. And there's also an amplification. And so what that amplification is, and I'm going to exaggerate here, but if the host software is 100% compliant or 99.999% compliant, and it's only writing maybe a 4K sector out of order once in a while, the cost to reclaim that one 4K sector is to unblend an entire zone. Again, it could be hundreds of megabytes. So there are several costs associated with host-aware. Advantages with host managed, this goes to my simplification point, is the host has control over the behavior. The latencies are controlled now by the host. The host is going to be doing the garbage collection of the read modify writes. It's a simpler device, lower power, and no write amplification. And where WSD sees these types of host-managed device going is we're starting in the tier 3, the archive area, but we also see a very good potential for these to go to the tier 2 area of storage. So I presented the easy drive case, and now Albert's going to tell us how it works.
Yeah. So I think there's a saying in computer science that anything could be solved with a layer of interaction. So if you look at the orange box here, this is where we look at potential places where we could address this smartness of not being able to modify what you have written. So obviously, if I'm missing a column on the very left, that would be a device managed solution, right? So everything is actually being done. All this is handled by the drive firmware. Obviously, there's a lot of benefits. It's backward compatible. However, you no longer have application level semantics, right? So if you are saving a file of a cat running on a unicorn with an RPG, some very important information, you want to save it quickly, the drive has no knowledge of that. All you get is a SCSI read write command. So if you go one level higher, where we have here the DM SMR, we're looking at integrating into the block device layer of, in this case, a device mapper layer of Linux. So that as read-write command comes down from the file system layer, we actually handle it in the block layer, where such that any file system could be running on above it, or application could strictly access a virtual device that allows random write behavior. And on top of that layer, we actually looked into sort of an SMR-friendly file system. So anything that's log structure, for example, so things like LTFS or NILFS, where it's actually written consecutively and comes back. So we actually tried that. However, that also has a drawback of what happens if you don't use that particular file system. You want to stick with XFS or EXT. So HGST actually has a libzbc library, which allows you to access the SMR device through a user space library, and we actually have written our own applications to run on top of that. However, that requires recompiling our application software to run against the libzbc library. So there's a drawback in terms of that as well. And finally, we also looked at having the application be SMR aware, be enlightened, to write, to be aware of the zones, and that you can no longer modify what you've written. However, that's very good in terms of if you only have one application. However, that's not very scalable when you have a host of other applications you want to run on top of SMR device.
So, said earlier, SMR has been evolving for quite some time now. We've been at it for a while. Several years ago, for reference, we did LTFS, which is what Albert talked about. Next year, we showed that a device, an SMR device, could be made to be, 99.99% compatible with NILFS. What's going on today? That's what's important. So today, actually, in Boston, there's a Linux conference going on. It's the LSF MM Summit. What's going on there is a continuation of what happened at that summit last year. And last year, the Linux guys invited the hard drive guys to come and visit and talk about SMR and hopefully come to a solution to the problem, right? And so what the message was there was that nobody was volunteering to change their file systems. ext4, ButterFS, XFS, nobody was offering that. But what they did offer, what was on Albert's chart, is a consensus that the device mapper was the proper layer to handle this problem, the sequentialness. And so I'm eager to look at my emails this evening, or actually after tomorrow, to see what the latest developments were out of that activity. But if you're interested in this, you probably want to get on some email distributions for the LSFMM, for the device mapper in particular. An activity there. We have some partners who are there. So I expect the scale solutions are probably going to come out of that group. Oh, and then Albert here is doing his device mapper, so that will be there, not yet, but soon. Bcache is another SMR-friendly layer to put in front of a host-managed SMR. ButterFS and ZFS are probably the most friendly SMR natively SMR-friendly file systems, and so people are actively working on that. And then SUSE, as of October, was presenting significant progress with host-managed SMR. They're also talking this week, so we'll look for their GitHub updates there. And then last part is where WD's playing here. So, you know, we firmly support the ZBC ZAC spec. We've championed the specification through T10. Curtis Stevens, WD guy, is authoring the spec. We talked about the benefits of SMR, and the status of current standardization activity is the proposals are complete at this point. ZBC letter ballot has occurred in January. It was accepted, and we're expecting the SATA version of that, or the ZAC version of that, to follow by 3 to 6 months. So things are going pretty well there. Are there any questions?
Since Flash is becoming this faster than this is okay, why don't you just leverage Flash stacks?
Flash stacks or tape stacks?
Because Flash has been
So I guess one familiarity I have is the Flash, the F2FS file system. Is that the one you might be thinking of? So we did look at that. We were aware of it about 2 years ago. When we dug into it, we found that the granularity of garbage collection was happening at about 2 megabytes, and that was hard-coded throughout. In an earlier slide, we talked about our granularity is probably going to be in the 200 megabyte range. So we would love to do that. Somebody from Seagate was presenting earlier, I think it came from Facebook, a Facebook driver. I'm not aware of that, but that might be some other Flash opportunity leverage. But any other questions? Thank you.
Thank you, Jane. All right, so you're a little bit ahead of time, that's good. So last but not least, we have another topic, which is SMR again. So we have HGST doing, so you have your presentation. Okay. Do you need HDMI or?
It's like it's a HDMI with mini.
Oh, mini HDMI.
It does HDMI.
Oh, okay. And again, for presenters, if you, as soon as I receive the presentations in PDF format, I will publish it. So please send me PDF format your presentations.
Okay, can you hear me? That working? Yeah, great. Okay, so I guess you've heard a lot about SMR already today. I'll add maybe another layer of SMR. Basically, this presentation will be split in two parts. At the beginning, I'll look at kind of a generic SMR properties and what does mean for the drive and eventually for the system. And the second part, I'll show what HDST has been doing to try to make SMR HDDs actually usable in a system. So first, how do we get SMR and what does it give our customers? Why would we want SMR? Well, oh yeah, I forgot about that. So you've all seen all of it, and we go to the next one. So shingle recording, you know what it is by now, but in the past for conventional perpendicular magnetic recording, it was possible to write data in discrete tracks that can be updated randomly. Any location within a track can be updated, and there is no issue with overriding the other tracks from a system standpoint. Now with SMR, we add a new property to the drive, which is that this data is going to be written in zones of overlapping tracks. If you were to try to overwrite this sector right in the middle here, then some of the data would be overwritten, and so you would lose your data. So you don't want to do it. You will have to make sure that data gets updated in those zones in a sequential manner. Everything needs to be written sequentially within the zone. Okay. Now, why do that? Well, the main reason for going to SMR is that it actually allows us to bring multiple technologies to HDDs and to basically get better capacity and overall better value. And this, in some way, SMR is a similar multi-generational technology like Helium is for HDST. So if you look at future recording technology like heat-assisted magnetic recording, two-dimensional magnetic recording, or patterned media, which are promising to bring much higher densities, those technologies are made much more feasible when implemented in conjunction with SMR and Helium as well. So the main point that I'm trying to convey in this slide is that thanks to SMR and Helium, we can have both reduced risk and potentially higher areal density in the future. And so without compromising on reliability or other standard parameters of this drive, the way they are built. Okay, so there are three types of SMR implementation that I'll go into a little bit of detail about. The first one is what we call drive managed, basically requiring no host software stack change. The drive manages everything about the fact that those zone exists. It will always write in a way that's commensurate to what the media is able to take, and it will expose still the standard interface to the host. So the drive extracts everything out from the host. Now, if the host were to be modified slightly, the host software were to be modified slightly, performance would be better, performance could be more predictable. Without doing so, there may be some variation in performance in a way that is hard to predict. Now, the second approach is to not abstract anything out in the drive layer, but to actually let the host control all this writing in tracks. And this is what host managed SMR is trying to provide. Now, the host needs to change, and this is why the interface is actually different. We're talking about ZBC and ZAC devices, so ZBC for SCSI or SAS, and ZAC for SATA, which exposes those sequential write-only zone. If the host were to try to write at a location that is not a write pointer for such a zone, then the command would be aborted, which is different behavior from normal SATA or SAS HDDs. Now, There is no specific recommended host changes. Those changes have to be made as part of the requirement. And the drive itself can be much simpler, and the performance can be much more consistent because the host actually knows when it's going to do some garbage collection at some layer. It will have to issue those IOs to the drive, and the drive will just respond to those IOs without having any further background garbage collection. The third approach is what's called host-aware, which is basically drive managed, but still exposes some information about where those zones are and where the right pointer may be, so that the host software can issue IOs in a way that is most reasonable for the drive implementation to handle it. Now, as you can see, this requires, or this does not require changes, but without the recommended changes, the performance may be unpredictable. And if you look at those changes for both host-managed and the host-aware, those changes are actually the same. So if you do the work for a host-managed device, you'll be ready to deal with host-aware devices as well, in a way that will provide you the optimal performance. Now, what does this really mean? If you look at the small graphic there, you see that there's a set of IOs here that are set in a continuous manner, increasingly. So there's no issue there for a host-managed device. It just gets written normally, both in the drive-managed, in the host-aware, or in the host-managed. This IOs, this one and this one are contiguous, but there, as you see, there's a skip here. In a host-managed device, this would not be acceptable. It would get an error, and so you have to make sure that the host software stack is not going to issue such an IO. In the host-aware case, what's going to happen is those IOs will be treated as a regular sequential write-only zone. Those IOs as well, because they are contiguous, but this one will cause this specific zone to go into drive managed mode, where basically the drive deals with the fact that the IO was not at the right location. Okay. So eventually, it is quite possible that the industry will migrate to host-aware keynote recording drive. However, in the short term, what we've seen is that the modification that would be required for host-managed actually would carry over very well into host-aware drives eventually. And for any application that requires the best possible performance out of a drive, even a host-aware drive, most modification would need to be done anyway. Now, as I mentioned, in the second part of this presentation, I want to go over what HDST has done to try to provide a software stack for those host-managed devices. Okay, so we have this project that we call libzbc, where we have implemented a library, an SDK, which application can use to access host-managed SMR devices, and actually host-aware SMR devices as well. This library provides a way to access the zone information that the report zone command returns, and it provides a way of issuing IOs. All this through the SGIO interface to issue directly SCSI commands to the drive. So it bypasses a lot of the software stack, as is shown here. In the cases where you're talking to a ZAC device or you're talking to a ZBC device, basically you issued through this library with IOs issued directly to the SCSI layer in the internal. We also have an emulation driver which allows you to use a regular disk and still use the same interface at the library level. Now this is what the library interface looks like. You basically have an open and close, very standard. Get device information, return some information about the SMR device. ZBC report zones is just yet another layer that actually exposes to the application the report zones output, report zones SCSI or ZAC output. Reset right pointer allows the application to reset the right pointer for a given zone. And finally, key reads and key writes are used for actually doing IOs to such a device. Now, as I mentioned, we have this interface emulation mode. The main goal is that for people who want to develop an application that will eventually work on single recording drive with a ZBC or ZAC interface, it is useful to be able to do that, to do this development in an environment that may not have those drives yet. And so this emulation mode basically emulates a host managed device and enforces the constraints that the host managed device will enforce. So if you try writing beyond the write pointer for a sequential write-only zone, then you will get an error at the library level. Obviously, this requires first setting the property of such a device, so how many zones, what the size of the zones are, where do they start, and so on. And so there's an extra set of commands, which is the TBC set zones to configure the device, or in this case, it can be a file, it can be a regular PMR device, doesn't matter. And finally, to set what the location of the write pointer at the start of the experiment should be.
What kind of performance trade-off would we expect if there was an emulated SMR device on a PMR device?
This one thing I should add is this library does not attempt to model the performance change variation that you may get with the actual SMR device. If you were to use this on an SMR device, you will be able to, on a non-SMR device, you will be able to do writes the same way that you would do writes on a PMR drive. So if you are able to sequentially write to a drive at, I don't know, 190 to 100 megabytes a second, this is also what you would get there on a regular drive. Actually, interestingly, you could run that on top of a SSD or even on a RAM disk, and then you would get great performance. But so this does not attempt to simulate the performance characteristic of the SMR drive. It's just exposing. This way towards talking directly to a block layer?
Yeah.
Well, not really. Actually, interestingly, is this emulation is actually done on top of a block layer rather than SGIO. So this actually goes through the page cache, goes through the standard command issuance stack in Linux. And so you will get very similar performance to what you would get if you were just to do writes and reads directly to a block device or to a file. The library does very little. It just checks the pointer and whether the command should be allowed or not. So that should be really, really minimal performance impact if you don't see it. Right, and the main point of this emulation mode is to allow application development before drives may be available. Okay, where can you get this? Well, it's on GitHub, so github.com/htst/ZBC, and you can download all the software. Now, what I presented was kind of an SDK to use SMR drives, and we have a little bit more than that. We do have a few command line tools. So this one can be used for actually retrieving the information from those commands, as I described previously, the report zones, the reset write pointer, reading the zone, writing the zone. Those can be directly called from the command line and allow you to read the data or write the data to the drive. We also have, this is one example of the report zone command and its output when issued to a ZAC device. So you can see the zones being reported. What type of zone, what the condition of the zone, what the start location is, how many sectors the zone is made of, and finally what the location of write pointer. In this case, it's all in the beginning of the zone anyway. And the equivalent tool as a GUI, which shows you, well, this drive had the first n zones that have been fully written. Oh, sorry, those zones are actually conventional recording zones. So those are zones that can be randomly written. All those ZBC and ZAC devices have the possibility of having conventional zones that can be randomly written. And those are the sequential write-only zones, and the red ones are those that have been fully written. And green is just the data, those that have not been written yet.
How are the zones allocated for drive? Is that fixed or dynamic?
Yeah, so I guess that's going to potentially be manufacturer dependent, but in practice, there is no requirement for those zones to be modifiable. So it might be just set by the drive manufacturer, and report zones only allows you to get what this setup of zone is, and the software stack will have to deal with that. Okay.
You can theory that it could be dynamic.
It could be, yeah. LKVS is another tool that we are giving with our SDK. So this is as we expect, most of the interest in those drives do not actually be in building general purpose file systems, but more to use it as a backend for maybe an object store or key value store. We actually built this small key value store that we call linear key value store. Linear is kind of a bit of a misnomer, but the main point was to try to show a key value store that tries to approach the best part of performance that could be unique and full metadata as possible. ABS is built on top of our libzvc and has a standard key value store interface where you can do puts of key value pairs and getting those afterwards. So again, this is a GitHub if you're interested in looking at it. It works there. It's shown as working on a ZBAC device. Obviously, it works there, but it could also be configured to work on a emulated device using our libzvc emulation. And if you come to the HGST booth tomorrow, you can see LKVS being used for the demo that streams some. Okay, that's it.
Any questions? Everybody's tired.
Great, yes. Thank you.
Oh, here you go. Sorry. Two questions.
Sorry. Sorry, I guess the beginning of the question.
The question that your description of the host-aware SMR architecture or construct, do you think it's more like a host child-managed SMR with some special mode allows performance mode, or the other way around? It's more like a host-managed construct with some error handling assist?
So, because host-aware needs to support any possible IOs, it will have to have what's equivalent to a fully drive managed solution. In worst case, the application decides not to care at all about any of this ZBC stuff and just writes randomly to it. So if someone were to use such a device this way, then the device needs to deal with it, which means you need to have some kind of full drive managed solution internally. Now, the main point of host-aware is that given that you have such a solution, using such a device should be done in a way that is reasonable so that you will get reasonable performance. And DAC and so on, CVC allow the drive to expose sufficient information for the software stack to take advantage of that and make life easier for the device. I don't know if that answers your question.
Kind of. So in the T10, T13 committee, is there any more clear definition of host-aware, or just very funny that allows the zones?
Oh, no, I think host-aware is pretty well defined. It's in T10 and T13. It says that basically it's a device for, it talks of zones. So for the host-aware devices that has zones that are sequential write preferred, it is allowable for the host to send random write IOs to such a zone. It's just preferred. So if a host were to send sequential commands, then the device would be a lot happier, but it's possible for the host to send anything.
I just want to make sure I understood your vision. You're enrolling host managed today, and so the software guys have to get 100% compliant to make that work.
That's right.
But then you're going to follow that up with host aware. What's the reason to follow up with host aware if the guys have already written 100% compliant software?
Well, because so right now it's allowing only a very limited set of applications for which the software development is doable in a reasonable amount of time. So you could imagine having done so for some applications, but still having some things that may not be fully compliant, in which case you may be ready to pay the penalty of having some more general file system or solution on top of it eventually. So we're perfectly aware that right now it's very limited use case for those who are willing to go to a set of modification that's outlined here. And all I wanted to say is, if you've done those modifications, then in the future, it's future-proof because you can still use those same modification on host-aware. It does not hurt you on host-aware. It's actually good for you in host-aware. That's all I was trying to outline.
Is it safe to say that if you have an application that is sensitive to predictable performance, that the application itself has to be SMR friendly?
So again, it depends on what we mean by the type of device we're using, but I'm assuming you're talking about drive managed.
Regardless of whether it's drive managed, host aware, or host managed. Right. That the application has to be SMR friendly, meaning it's predominantly sequentially write data.
Yes.
Not a whole lot of capacity reuse, really, capacity reuse. But in order to get predictable performance for that application, is it safe to say that that application has to be SMR friendly?
Yes.
So it's just a matter of something that's going to, if the application is not SMR friendly, something has to do work underneath it. Whether it's if it's host managed, there's a layer underneath that's managed.
That's right.
If it's drive managed, the drive is doing the work, right?
That's right.
Any other questions?
Hi, so maybe expanding on the gentleman's question over there, if you already made all the modifications for host managed on the host side, then would you expect a host aware drive to have the same performance as a host managed drive, or not?
Yeah, that's a great question. I can't really speculate on what manufacturers may have done on specific applications, so it's hard to say.
Comment on the Western, the HGST flavors?
So, yeah, I don't know if the specific performance I can make any statement about. All I can say is really, if you've done the modification for host managed, you should be able to get whatever is the best performance you can get out of your host aware drive eventually when you get your host aware. I don't know if I can compare host aware versus host managed because there are just so many parameters that go into making the performance of the drive versus another. But all I can say is that whatever is performance for sequential throughput and so on will be on your host aware drive. You'll max that out if you deal with the drive in a host managed way.
So that means that maybe host aware drive is not based on host managed drive.
I'm not exactly sure how to answer that. I mean, it's internally the first part of the presentation, those zones of overlapping tracks. This will be true for host managed and host aware SMR drive and drive managed for that matter. How the IOs may be indirected or whatever host aware implementation may be doing, that's highly manufacturer dependent, so I can't really comment all that much.
Great. Thank you again. No worries.
Yeah, that's right.
So, thanks a lot for sticking so long. I know it was kind of tiring, but I think we had a great set of presenters today, and we'll have great presentations tomorrow as well. I think we will start at 3:30, but check the schedule again because we have to shift the schedules a little bit. I'm not sure if they did the same thing for tomorrow. But tomorrow everything starts with the summit itself, and then in the afternoon, around 3 or 3:30, we will meet here. With that, thank you very much, and see you tomorrow. Thank you. So,